What if everything we think we know about the universe is built on a shaky foundation? What if the laws of physics, those unbreakable rules we've come to rely on, are not laws at all, but more like suggestions? It sounds like the stuff of science fiction, but some of the brightest minds in physics are beginning to entertain this radical possibility. From the strange behavior of particles at the quantum level to the mind-bending implications of alternate dimensions, there's a growing sense that the universe might be far more flexible than we've ever imagined. This isn't just about rewriting textbooks, it's about redefining reality itself. So, what does it mean if the laws of physics are more like guidelines? And how could this idea change everything from the way we explore space to the way we understand our place in the cosmos? Buckle up, because we're about to dive into some of the most daring theories in modern science. And by the end of this journey, you might just find yourself questioning everything you thought was certain. Let's start with the question that sparked this entire exploration. Why does this idea matter, and what could it mean for the future of humanity? To truly grasp why the laws of physics might be more flexible than we've been taught, let's take a step back and look at how we got here. For centuries, the study of physics has been rooted in the idea that the universe follows strict, unchanging rules. It all began with Isaac Newton, whose laws of motion and universal gravitation laid the groundwork for classical physics. Imagine the awe people felt when Newton explained why apples fall to the ground or how planets orbit the sun. It was as if humanity had unlocked the instruction manual for the cosmos. These laws weren't just groundbreaking, they were absolute, or so it seemed. Then came Albert Einstein, who turned the scientific world on its head with his theory of relativity. Suddenly, space and time weren't separate entities but a single, interwoven fabric. Gravity wasn't a force in the traditional sense, but a curvature in this fabric caused by massive objects. Einstein's work didn't just refine Newton's ideas, it completely redefined them. Yet, even relativity operated under the assumption that the universe follows certain immutable rules. For decades, these frameworks, Newtonian mechanics and Einstein's relativity, formed the bedrock of our understanding, giving us the tools to predict everything from the motion of planets to the behavior of light. But here's the twist: as we've pushed the boundaries of science, cracks have started to appear in this seemingly unshakable foundation. Take quantum mechanics, for example. At the smallest scales, particles don't behave like objects in Newton's or even Einstein's worlds. They can exist in multiple states at once, disappear and reappear in different places, and even influence each other instantaneously across vast distances. This bizarre behavior defies everything classical physics taught us, suggesting that the rules we thought were universal might only apply under certain conditions. And it's not just quantum mechanics that's raising questions. Dark matter and dark energy, which together make up about 95% of the universe, remain largely mysterious. We know they exist because of their gravitational effects, but we don't fully understand what they are or how they work. These unknowns hint at the possibility that our current laws of physics are incomplete, or perhaps just one piece of a much larger puzzle. So, what does this mean for the idea that the laws of physics are mere suggestions? It means that the rules we've relied on for centuries might not be as rigid as we once believed. Instead, they could be more like guidelines, useful approximations that work well in certain contexts but break down when we explore the extremes of the universe. As we delve deeper into the mysteries of space and time, we're beginning to see that reality might be far more dynamic, more unpredictable, and more fascinating than we ever imagined. And that's just the beginning. Now, let's zoom in on the moment when the cracks in our classical understanding of physics first began to show the birth of quantum mechanics. This isn't just a story about new discoveries. It's a story about how the universe revealed itself to be far stranger, far more unpredictable than anyone had ever dared to imagine. At the heart of this revolution is a simple yet mind-bending idea. At the smallest scales, particles don't follow the same rules as the objects we see in our everyday lives. Instead, they operate in ways that seem to defy logic, challenging the very notion of fixed, unchanging laws. Take the double-slit experiment, for example. At first glance, it seems straightforward. Shoot particles like electrons through two slits and see where they land on a screen. But here's where things get weird. When you don't observe the particles, they behave like waves, creating an interference pattern on the screen as if they've passed through both slits at once. Yet, the moment you try to measure which slit a particle goes through, it suddenly acts like a single, discrete object. It's as if the particle knows it's being watched and changes its behavior accordingly. This bizarre phenomenon hints at something profound. The act of observation itself might shape reality, suggesting that the universe is far more interactive and far less deterministic than we've ever thought. Then there's the concept of superposition, which takes this strangeness to a whole new level. In the quantum world, particles don't have to exist in just one state at a time. Instead, they can exist in multiple states simultaneously, like a coin spinning in midair, neither heads nor tails but both at once. This idea was famously illustrated by Schrödinger's thought experiment with a cat, which could theoretically be both alive and dead until someone opens the box to check. While the cat scenario is hypothetical, superposition is very real, and it's been demonstrated in countless experiments. It forces us to ask, if particles can exist in multiple states at once, what does that say about the nature of reality itself? But perhaps the most baffling aspect of quantum mechanics is entanglement. Imagine two particles that are so deeply connected that no matter how far apart they are, whether it's across a room or across the universe, they instantly influence each other's behavior. Einstein famously called this spooky action at a distance, and it's a concept that even he struggled to accept. Yet, experiments have repeatedly confirmed that entanglement is real, showing that particles can share information faster than the speed of light. This doesn't just challenge our understanding of physics, it shakes the very foundation of how we think about space, time, and causality. And let's not forget the uncertainty principle, which tells us that there are fundamental limits to what we can know about a particle's properties. You can't measure both its position and momentum with perfect precision. The more you know about one, the less you know about the other. This isn't a limitation of our tools or our knowledge, it's a fundamental property of the universe. It suggests that at the quantum level, reality is inherently fuzzy, governed not by rigid laws but by probabilities. So, what does all this mean for the idea that the laws of physics are mere suggestions? Quantum mechanics shows us that the universe doesn't play by the same rules at every scale. The orderly, predictable world we experience in our daily lives might just be a special case, a simplified version of a far more complex and dynamic reality. As we continue to explore the quantum realm, we're left with more questions than answers, but one thing is clear. The universe is far stranger, far more flexible, and far more mysterious than we ever imagined. And this is just the tip of the iceberg. But what if our universe isn't the only one? What if, instead of a single cosmic stage with fixed rules, there's an endless array of universes, each playing by its own unique set of physical laws? This is the heart of the multiverse theory, a mind-bending idea that suggests our universe might be just one among an infinite number of others, each with its own distinct properties. Imagine a cosmic tapestry where every thread represents a different universe, some with gravity so weak it barely exists, others with stars that burn in colors we can't even comprehend. This isn't just science fiction, it's a serious scientific proposal that's gaining traction among physicists, and it could completely upend our understanding of reality. The idea of a multiverse isn't just a wild guess, it's rooted in some of the most advanced theories in modern physics. Take cosmic inflation, for example. This theory explains how the universe expanded exponentially in the moments after the Big Bang, growing from a tiny speck to a vast cosmos in a fraction of a second. But here's the twist. Some versions of inflation suggest that this rapid expansion didn't just happen once. It could have happened countless times, creating bubbles of space-time that each became their own separate universe. In this scenario, our universe is just one bubble in a frothy sea of cosmic foam, each bubble potentially governed by its own unique set of physical laws. Then there's string theory, a framework that attempts to unify all the forces of nature into a single, elegant description. String theory proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. But for this theory to work, it requires extra dimensions far more than the 3 spatial dimensions we're familiar with. These extra dimensions could be curled up and hidden from our view, but they might also host other universes, each with different configurations of strings and consequently different physical laws. It's a staggering thought. The constants we take for granted, like the speed of light or the strength of gravity, might not be universal at all, but instead just one set of parameters among an infinite array of possibilities. So why does this matter? For one, the multiverse theory could help explain some of the most puzzling features of our own universe. Take the so-called fine-tuning problem, for instance. The fundamental constants of nature, things like the charge of an electron or the density of dark energy, seem to be precisely calibrated to allow for the existence of life. If these values were even slightly different, stars wouldn't form, atoms wouldn't hold together, and life as we know it would be impossible. But in a multiverse, this fine-tuning isn't so mysterious. If there are countless universes with different constants, it's no surprise that at least one would have the right conditions for life. We just happen to live in that one. But the multiverse theory doesn't just solve problems, it raises profound questions. If the laws of physics can vary from one universe to another, what does that mean for the idea of universal truths? Are the laws we've discovered in our universe truly fundamental, or are they just local rules that apply to our particular corner of reality? This challenges the very foundation of science, which has always sought to uncover universal principles that apply everywhere, always. If the multiverse is real, then those principles might not be as universal as we thought. And then there's the question of evidence. If other universes exist, how could we ever detect them? Some scientists have proposed looking for fingerprints of collisions between our universe and others, perhaps imprinted in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Others suggest that gravitational waves, ripples in space-time caused by violent cosmic events, might carry clues about the existence of parallel universes. While these ideas are still speculative, they represent the first steps toward testing a theory that, for now, remains largely theoretical. The multiverse theory isn't just a radical reimagining of reality. It's a challenge to our understanding of what it means to exist. If there are infinite universes, each with its own set of physical laws, then our universe is no longer the center of everything. It's just one possibility among an endless sea of others, each with its own story, its own rules, and perhaps its own forms of life. This idea forces us to confront the limits of our knowledge and the vastness of what we have yet to discover. And as we continue to explore the mysteries of the cosmos, the multiverse theory reminds us that reality might be far stranger, far more diverse, and far more wondrous than we've ever dared to imagine. What if the universe isn't made of particles at all, but of something far more subtle and dynamic? Enter string theory, a bold and revolutionary idea that suggests the fundamental building blocks of reality aren't tiny dots of matter but incredibly small, vibrating strings. These strings, so tiny that they'd be impossible to see even with the most powerful microscopes, are thought to vibrate at different frequencies, creating all the particles and forces we observe in the universe. It's a concept that sounds almost poetic, a cosmic symphony where every note corresponds to a different particle or force. But beneath this elegant idea lies a profound implication. If string theory is correct, the laws of physics as we know them might not be fundamental truths but rather emergent properties of these underlying vibrations. To understand why this matters, let's take a closer look at what string theory is trying to achieve. For decades, physicists have been searching for a way to unify the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. Each of these forces operates under its own set of rules, and while we've made incredible progress in understanding them individually, they don't quite fit together into a single, cohesive framework. String theory offers a potential solution by proposing that all these forces arise from the same underlying mechanism: the vibrations of strings. In this view, the differences between gravity and electromagnetism, for example, aren't due to separate laws but to the unique ways these strings vibrate and interact. But string theory doesn't stop there. One of its most startling predictions is the existence of extra dimensions far more than the three spatial dimensions we experience every day. According to the theory, these extra dimensions are curled up and hidden from our perception, much like the way a garden hose might look like a one-dimensional line from a distance but reveal its true cylindrical shape up close. These hidden dimensions aren't just theoretical oddities, they're essential for the math of string theory to work, and if they exist, they could completely reshape our understanding of reality, suggesting that the universe is far more complex and multifaceted than we've ever imagined. So, what does this mean for the idea that the laws of physics might be emergent rather than fundamental? If the universe is built on vibrating strings, then the rules we've come to rely on, like gravity or electromagnetism, aren't the ultimate truths but rather the consequences of how these strings behave. It's like watching the surface of a pond and noticing the ripples and waves, but not realizing that they're all caused by the same underlying motion of water molecules. In this view, the laws of physics aren't handed down from on high. They're patterns that emerge from the intricate dance of strings. This idea also raises fascinating questions about the nature of reality itself. If the laws of physics are emergent, could they change under different conditions? Could there be regions of the universe where the strings vibrate in ways that produce entirely different sets of physical laws? String theory doesn't just challenge our understanding of the universe. It opens the door to a cosmos that's far more dynamic and varied than we've ever imagined. Of course, string theory is still a work in progress, and there's much we don't yet understand. For one, the math involved is incredibly complex, and testing the theory experimentally has proven to be a significant challenge. But even if string theory isn't the final answer, it represents a profound shift in how we think about the universe. It reminds us that the laws of physics might not be fixed and immutable, but rather the result of deeper, more fundamental processes that we're only beginning to uncover. And as we continue to explore these ideas, we're left with a sense of wonder, a reminder that the universe is far stranger, far more intricate, and far more beautiful than we've ever dared to imagine. Picture this: everything we can see, stars, planets, galaxies, even you and me, makes up just 5% of the universe. The rest, it's a cosmic mystery hidden in plain sight. Enter dark matter and dark energy, the enigmatic forces that dominate the cosmos yet remain utterly invisible to us. These aren't just gaps in our knowledge, they're profound challenges to the very framework of physics as we know it. If the laws we've discovered only describe a tiny slice of reality, what does that say about the universe itself? And could these hidden forces be pointing us toward a deeper, more flexible understanding of how everything works? Let's start with dark matter, the elusive substance that makes up about 27% of the universe. We can't see it, touch it, or detect it directly, yet we know it's there because of its gravitational pull. Galaxies, for instance, spin faster than they should if only the visible matter inside them were holding them together. Without dark matter, entire galaxies would fly apart, their stars scattering into the void. It's like watching a car race around a track without a driver. You know something invisible must be steering it, even if you can't see what that something is. But here's the kicker: despite decades of searching, we still don't know what dark matter actually is. Is it made of particles we haven't discovered yet? Could it be something even stranger, defying our current understanding of matter entirely? Then there's dark energy, an even more baffling phenomenon that makes up a staggering 68% of the universe. Unlike dark matter, which holds galaxies together, dark energy seems to be doing the opposite, pushing the universe apart. In the late 1990s, astronomers discovered that the expansion of the universe isn't slowing down as everyone expected, but accelerating. Dark energy is the name we've given to whatever is causing this acceleration, but its true nature remains one of the greatest mysteries in science. Is it a property of space itself, as Einstein once suggested with his cosmological constant? Or is it something entirely new, a force we've yet to fully comprehend? Together, dark matter and dark energy paint a picture of a universe that's far stranger than we ever imagined. They challenge the notion that the laws of physics we've uncovered are universal truths. Instead, they suggest that these laws might only describe the visible tip of a much deeper, more complex iceberg. Think of it like trying to understand an ocean by studying only the waves on its surface. The currents, the depths, the life teeming below, all of it remains hidden, yet it shapes everything we see above. In the same way, dark matter and dark energy might be hinting at a hidden layer of reality, one where the rules are entirely different from what we've come to expect. This raises a tantalizing question. Could our universe be governed by a more flexible set of rules than we've realized? If dark matter and dark energy operate outside the framework of our current laws, does that mean those laws are incomplete or merely local? It's a humbling thought, one that forces us to reconsider our place in the cosmos. For centuries, we've assumed that the universe follows strict, unchanging rules. But what if those rules are more like guidelines, applicable only to the small fraction of reality we can observe? What if the rest of the universe operates under a completely different playbook? And then there's the question of stability. Dark energy, in particular, seems to be driving the universe toward an uncertain future. If its influence continues to grow, it could eventually stretch the fabric of space-time so thin that galaxies, stars, and even atoms are torn apart. On the other hand, if dark energy's effects weaken over time, the universe might collapse back in on itself in a big crunch. Either scenario suggests that the cosmos is far more dynamic and far less predictable than we've ever thought. It's a reminder that the universe isn't a static, unchanging entity, but a living, evolving system full of surprises. So, what does all this mean for our understanding of physics? Dark matter and dark energy aren't just puzzles to solve, they're windows into a deeper reality. They remind us that the universe is vast, mysterious, and full of possibilities we've yet to explore. And as we continue to study these hidden forces, we might just find that the laws of physics aren't set in stone, they're more like suggestions waiting to be rewritten. The question is, are we ready to embrace a universe that's far stranger, far more flexible, and far more wondrous than we've ever imagined? The journey to find out is just beginning. What if the universe isn't just a random collection of rules and forces, but a carefully crafted stage perfectly set for life to emerge? This is the heart of the Anthropic Principle, a thought-provoking idea that suggests the laws of physics aren't arbitrary, but finely tuned to allow for the existence of life as we know it. At first glance, this might sound like a philosophical musing, but it's a concept that has profound implications for how we understand the cosmos. If the universe is tailored for life, what does that say about the nature of reality itself? And could this fine-tuning be more than just a cosmic coincidence? To unpack this idea, let's start with the basics. The Anthropic Principle comes in two main flavors, the weak and the strong. The weak Anthropic Principle simply states that the conditions we observe in the universe must be compatible with the existence of observers like us. It's a bit like saying, of course we find ourselves in a universe that supports life. If it didn't, we wouldn't be here to notice. This version is almost a tautology, but it's useful for framing scientific questions. Why, for example, does the universe have just the right amount of dark energy to allow galaxies to form? The weak Anthropic Principle suggests that if it didn't, we wouldn't be around to ask the question. The strong Anthropic Principle, on the other hand, takes things a step further. It proposes that the universe must have properties that allow life to arise. This version is far more controversial because it implies a kind of cosmic purpose, a universe designed with life in mind. While this idea might sound like it belongs in the realm of philosophy or theology, it's a hypothesis that some scientists take seriously. After all, the constants of nature, like the strength of gravity or the charge of an electron, are incredibly precise. If any of these values were even slightly different, stars wouldn't shine, atoms wouldn't form, and life as we know it would be impossible. So, is this precision just a lucky accident, or is there something deeper at play? One possible explanation for this fine-tuning is the multiverse theory, which we touched on earlier. If there are countless universes, each with its own set of physical laws, then it's no surprise that at least one of them would have the right conditions for life. In this view, our universe isn't special, it's just the one we happen to inhabit. But this raises another question. If the laws of physics can vary from one universe to another, does that mean they're not fundamental truths but rather local rules, shaped by the unique conditions of each universe? This idea challenges the very foundation of physics, which has always sought to uncover universal principles that apply everywhere, always. Another angle comes from the idea of emergence, the notion that the laws of physics aren't fixed but arise from deeper, more fundamental processes. If this is true, then the fine-tuning we observe might not be a feature of the universe itself, but a consequence of how complexity arises from simpler rules. Think of it like a sandcastle on a beach. The shape of the castle isn't determined by the sand grains themselves, but by the way they're arranged. In the same way, the laws of physics might emerge from the interactions of more basic components, like strings or quantum fields, creating a universe that's finely tuned for life as a result. But the Anthropic Principle isn't just about science, it's also deeply philosophical. It forces us to confront questions about the nature of existence and our place in the cosmos. If the universe is fine-tuned for life, does that mean life has a special significance? Or is it simply a byproduct of the way things are? These questions don't have easy answers, but they invite us to think more deeply about what it means to exist in a universe that seems so perfectly suited for us. At the same time, the Anthropic Principle challenges us to rethink the idea of fixed, unchanging laws. If the universe is fine-tuned, could that fine-tuning change over time? Could the laws of physics evolve as the universe itself evolves? This idea is still speculative, but it opens up fascinating possibilities. Perhaps the universe isn't a static entity governed by rigid rules, but a dynamic, evolving system, constantly adjusting to create the conditions necessary for life. Ultimately, the Anthropic Principle reminds us that the universe is far more mysterious and complex than we've ever imagined. It doesn't just challenge our understanding of physics, it challenges our understanding of ourselves. Are we the result of a cosmic accident, or is there something more at work? As we continue to explore these questions, we're left with a profound sense of wonder, a reminder that the universe is not just a place we inhabit, but a story we're still learning to read. And in that story, the laws of physics might not be the final word, they might just be the beginning. What if everything around us, the stars, the planets, even the air we breathe, isn't real? What if the universe is nothing more than an incredibly advanced simulation, and the laws of physics are just lines of code in a cosmic program? This might sound like the plot of a sci-fi movie, but it's a serious idea that some scientists and philosophers are starting to take seriously. Known as simulation theory, it proposes that our reality could be a digital construct created by an intelligence far beyond our understanding. And if that's true, it would completely change how we think about the laws of physics and our place in the universe. The idea of simulation theory isn't new. Philosophers like René Descartes pondered whether reality could be an illusion centuries ago, but the modern version of this idea owes much to Nick Bostrom, a philosopher at Oxford University. In 2003, Bostrom proposed a thought experiment that's become the foundation of simulation theory. He argued that if a civilization ever reaches the technological level to create realistic simulations of entire universes, it's possible that the number of simulated beings could vastly outnumber those in the real world. If that's the case, the odds of us being in the original, base reality are incredibly slim. It's a startling idea, but one that's hard to dismiss outright. So, what evidence could support the idea that we're living in a simulation? One argument comes from the strange behavior of the universe at the smallest scales. Take quantum mechanics, for example. At the quantum level, particles don't behave like solid objects, but more like probabilities or waves until they're observed. This observer effect has long puzzled scientists, but some have suggested it could be a sign that the universe is running on a kind of computational framework. In a simulation, information doesn't need to be fully rendered until it's observed. A bit like how a video game only loads the parts of the world you're currently looking at. Could quantum weirdness be a hint that our reality works the same way? Then there's the idea of mathematical precision. The laws of physics are described by equations that are incredibly precise, almost as if they were written by a programmer. For example, the speed of light in a vacuum is exactly 299,792,458 meters per second, a constant that doesn't vary by even a fraction. This kind of precision is hard to explain as a natural phenomenon, but it makes perfect sense if the universe is governed by code. After all, in a simulation, constants like the speed of light would be hardwired into the program to ensure consistency. But simulation theory isn't without its skeptics. One of the biggest challenges is the sheer complexity of simulating an entire universe. Even if a civilization had the technology, why would they bother? Some argue that it's more likely they'd simulate smaller, more manageable worlds rather than an entire cosmos. Others point out that if we're living in a simulation, there should be glitches or errors in the code, tiny inconsistencies that reveal the artificial nature of reality. While some claim to have found potential glitches like anomalies in the cosmic microwave background radiation, these findings are far from conclusive. Still, the idea that our reality might be programmable raises fascinating questions about the nature of the laws of physics. If the universe is a simulation, then the rules we've discovered, gravity, electromagnetism, quantum mechanics, aren't fundamental truths but parameters set by the programmers. This opens up the possibility that these laws could be changed, updated, or even hacked. Imagine a future where we could manipulate the code of reality itself, bending the rules of physics to our will. It's a tantalizing thought, but one that comes with its own set of ethical and philosophical dilemmas. Simulation theory also challenges us to rethink what it means to exist. If we're living in a simulation, are we real? Do our thoughts, emotions, and experiences have any meaning, or are they just lines of code? These questions might seem abstract, but they have real implications for how we view ourselves and our place in the universe. They remind us that reality might be far more fluid and malleable than we've ever imagined. Whether or not simulation theory is true, it serves as a powerful reminder that the universe is full of mysteries we've yet to unravel. It pushes us to question our assumptions, explore new ideas, and remain open to the possibility that reality might be far stranger than we've ever dared to imagine. And as we continue to probe the nature of existence, one thing is clear: the laws of physics might not be as absolute as we once thought. They could be mere suggestions, lines of code in a cosmic program waiting to be rewritten. The question is, are we ready to embrace a universe where anything is possible? Only time and perhaps a few more lines of code will tell. What if time, that steady, unyielding force we've come to rely on, isn't as constant as it seems? We've all experienced moments that seem to stretch on forever, waiting in line, sitting through a dull meeting. But what if time itself can stretch, bend, or even loop back on itself? This isn't just a poetic thought, it's a scientific possibility that challenges one of our most deeply held assumptions: that time flows in one direction, like an arrow shot from the past into the future. But what if the arrow of time is more like a boomerang, capable of changing course or even returning to its starting point? Let's start with something we know for sure: time isn't the same everywhere. Thanks to Einstein's theory of relativity, we've learned that time can slow down or speed up depending on where you are and how fast you're moving. This phenomenon, known as time dilation, has been proven time and time again. For example, astronauts aboard the International Space Station age ever so slightly slower than people on Earth because they're moving at such high speeds. It's a small effect, but it's real, and it shows that time isn't the rigid, unchanging force we once thought it was. Instead, it's more like a river, flowing at different speeds depending on the terrain. But what if time doesn't just flow differently? What if it can flow backward? This idea might sound like science fiction, but it's grounded in some of the most advanced theories in physics. Take quantum mechanics, for instance. At the quantum level, particles don't always follow the rules of cause and effect. In fact, some experiments suggest that particles can move backward in time, reversing the usual order of events. It's as if the universe has a rewind button, allowing certain processes to play out in reverse. While this doesn't mean you'll be traveling back to your childhood anytime soon, it does hint at a deeper flexibility in the fabric of time. Then there's the concept of time loops, a favorite trope in movies like Groundhog Day or Tenet. But could such loops exist in reality? Some physicists think so. Closed time-like curves, as they're called, are theoretical paths through space-time that loop back on themselves, allowing an object, or even a person, to return to the same point in time. These loops aren't just mathematical curiosities, they're solutions to Einstein's equations of general relativity. Of course, creating a time loop would require conditions we can't yet replicate, like the intense gravitational fields near a black hole or the manipulation of exotic matter. But the fact that they're even possible suggests that time might be far more malleable than we've ever imagined. And what about alternate timelines? The idea of parallel universes, each with its own version of history, has been a staple of science fiction for decades. But it's also a serious scientific proposal rooted in the many worlds interpretation of quantum mechanics. According to this theory, every decision we make, every quantum event, splits the universe into multiple branches, each representing a different outcome. In one timeline, you might have chosen a different career path. In another, a key historical event might have unfolded in an entirely different way. While we can't hop between these timelines, their existence implies that time isn't a single, linear path but a branching tree full of possibilities. So, what does all this mean for the laws of physics? If time can stretch, loop, or branch, then our understanding of it might be far too simplistic. The arrow of time, the idea that time flows in one direction, might not be a fundamental law but a consequence of how we experience the universe. It's like watching a movie. From our perspective, the story unfolds in a specific order, but the film itself exists all at once, frame by frame. Could time be similar, with past, present, and future all existing simultaneously, and our perception of it merely a product of how we're wired to experience reality? These ideas don't just challenge our understanding of time, they challenge our understanding of the universe itself. If time isn't the rigid, unchanging force we've always thought it was, then the laws of physics might not be as absolute as we've assumed. Instead, they could be more like guidelines shaped by the conditions of our particular corner of reality. And as we continue to explore the mysteries of time, we're left with a profound question. What else might we discover about the universe when we stop assuming that time is set in stone? The answer could change everything we think we know about reality and our place within it. What if gravity, the force that keeps our feet on the ground and the planets in their orbits, isn't as unshakable as we've been led to believe? For centuries, gravity has been treated as one of the universe's fundamental constants, a force so reliable that it's become the backbone of physics. But what if it's not a fixed law? What if gravity is more like a suggestion, a rule that works well in certain contexts but breaks down when we look closer? This is the daring question some physicists are asking, and it's leading us to rethink one of the most basic forces in nature. Let's start with the story we all know. Isaac Newton gave us the first clear description of gravity when he saw an apple fall, and realized the same force must hold the moon in orbit around the Earth. His law of universal gravitation worked beautifully for centuries, explaining everything from tides to planetary motion. But then came Einstein, who showed that gravity isn't a force in the traditional sense. Instead, it's the result of massive objects warping the fabric of space-time, like a bowling ball sitting on a trampoline. This revolutionary idea, known as general relativity, has been confirmed time and again, from the bending of light around massive objects to the precise orbits of Mercury. Yet, even Einstein's theory isn't the final word. One of the biggest challenges to our current understanding of gravity comes from the cosmos itself. When we look at galaxies, we find something strange. They spin faster than they should. According to the laws of gravity as we know them, the outer edges of galaxies should move more slowly than the inner regions. But they don't. Instead, stars at the edges of galaxies zip around at speeds that defy our predictions. To explain this, scientists propose the existence of dark matter, an invisible substance that provides the extra gravitational pull needed to keep galaxies intact. But what if dark matter isn't the answer? What if instead our understanding of gravity is incomplete? This is where alternative theories come in. One of the most intriguing is modified Newtonian dynamics, or MN. Proposed in the 1980s, MN suggests that gravity behaves differently at very low accelerations, like those found at the edges of galaxies. In these regions, the force of gravity might not follow the inverse square law that Newton and Einstein relied on. Instead, it could weaken more slowly, providing the extra pull needed to explain the observed speeds of stars without invoking dark matter. While has its critics, it's a compelling idea that challenges us to think differently about gravity. Then there's quantum gravity, a field that seeks to unify general relativity with quantum mechanics. These two pillars of modern physics don't play well together. General relativity describes gravity on cosmic scales, while quantum mechanics governs the behavior of particles at the tiniest levels. But when you try to apply both to the same scenario, like the center of a black hole or the moment of the Big Bang, the math falls apart. Quantum gravity theories like loop quantum gravity and string theory suggest that gravity might not be a fundamental force at all, but an emergent property arising from more basic quantum processes. In this view, gravity is more like a wave on the surface of an ocean, a phenomenon that emerges from the interactions of countless individual particles beneath. So, what does all this mean for our understanding of gravity? If gravity is emergent, it might not be a fixed law, but something that changes depending on the scale or context. It could be a rule that works well in our everyday lives but behaves differently in the extreme environments of black holes or the early universe. This idea doesn't just challenge our textbooks, it challenges the very way we think about the universe. Are the laws of physics truly universal, or are they more like guidelines shaped by the conditions of the environment they operate in? And then there's the question of testing these ideas. How do we know if gravity is emergent or if dark matter is real? One approach is to look for discrepancies in the way gravity behaves in different settings. For example, some scientists are studying the behavior of galaxies in clusters, where the gravitational pull of dark matter should be strongest. Others are probing the tiny scales where quantum effects might reveal gravity's true nature. These experiments are pushing the boundaries of what we know, and they could lead us to a deeper understanding of one of the universe's most fundamental forces. Gravity is more than just a force, it's a window into the nature of reality itself. Whether it's a fundamental law or an emergent property, the way we understand gravity shapes how we see the universe. And as we continue to explore these radical ideas, we're reminded that science is never finished. It's a journey of discovery, full of surprises, challenges, and the occasional apple falling from a tree. The question is, are we ready to let go of what we think we know and embrace a universe where even gravity might be up for debate? Imagine an object so dense, so powerful, that not even light can escape its grip. Black holes are cosmic enigmas, regions of space where gravity is so intense that the usual rules of physics seem to break down. But what if these mysterious objects aren't just anomalies? What if they're windows into a deeper, more flexible understanding of the universe? At the heart of every black hole lies the event horizon, the boundary beyond which nothing, no matter, no light, no information, can escape. It's a point of no return, a place where our understanding of space and time reaches its limits. But here's the twist: the event horizon isn't just a barrier, it's a laboratory for testing the laws of physics. When matter crosses this threshold, it's stretched and compressed in ways that challenge everything we know about gravity, quantum mechanics, and even the nature of reality itself. One of the most perplexing questions about black holes is what happens to the information they consume. According to quantum mechanics, information can never be destroyed. It's a fundamental principle of the universe. Yet, when matter falls into a black hole, it seemingly vanishes, taking all its information with it. This contradiction, known as the information paradox, has puzzled scientists for decades. Stephen Hawking famously suggested that black holes might slowly evaporate over time, releasing energy in the form of what's now called Hawking radiation. But if that's the case, where does the information go? Does it get encoded in the radiation, or is it lost forever? This paradox isn't just a theoretical curiosity, it's a clue that our current laws of physics might be incomplete. But black holes don't just hide secrets, they also reveal profound insights. Take the concept of singularity, the point at the center of a black hole where density becomes infinite and the laws of physics as we know them cease to function. Singularities are places where general relativity and quantum mechanics collide, and their existence suggests that our understanding of gravity and space-time is fundamentally flawed. Some physicists believe that resolving the mysteries of singularities could lead us to a unified theory of quantum gravity, a framework that reconciles the large-scale forces of general relativity with the small-scale weirdness of quantum mechanics. Then there's the idea that black holes might not be the destructive forces we've always imagined. Some theories suggest that they could act as gateways to other regions of space-time or even other universes. Wormholes, hypothetical tunnels through space-time, are often linked to black holes, offering the tantalizing possibility of shortcuts across the cosmos. While these ideas are still speculative, they remind us that black holes might not just be endpoints, but also portals to new realms of physics. Studying black holes isn't just about understanding these bizarre objects, it's about pushing the boundaries of our knowledge. Every observation, every theory brings us closer to answering some of the biggest questions in science. What lies beyond the event horizon? How do gravity and quantum mechanics fit together? And could the extreme conditions of black holes reveal a more flexible, dynamic set of physical laws? As we peer into the depths of these cosmic mysteries, we're reminded that the universe is far stranger and more wondrous than we've ever imagined. Black holes aren't just challenges to our understanding, they're invitations to explore, to question, and to rethink what we thought we knew about reality. And in that exploration, we might just discover that the laws of physics aren't as rigid as we once believed. They're more like suggestions, waiting to be rewritten by the next great discovery. What if everything we see around us, the stars, the galaxies, even the screen you're looking at right now, isn't as three-dimensional as it seems? What if our entire universe is actually a two-dimensional projection, like a hologram? This might sound like a plot twist from a sci-fi movie, but it's a serious scientific proposal known as the Holographic Principle. And if it's true, it could completely upend our understanding of space, time, and the very nature of reality. To wrap your head around this idea, let's start with something familiar: a hologram. A hologram is a two-dimensional surface that encodes information in such a way that it appears three-dimensional when viewed under the right conditions. The holographic principle takes this concept and scales it up to cosmic proportions, suggesting that the entire universe might work the same way. In this view, all the information about the three-dimensional world we experience, every particle, every force, every event, is encoded on a two-dimensional surface at the boundary of the universe. It's as if reality itself is a kind of cosmic projection, with the laws of physics emerging from this lower dimensional framework. But how could this possibly work? The idea stems from some of the most cutting-edge research in theoretical physics, particularly the study of black holes. In the 1970s, physicist Jacob Bekenstein discovered that the entropy of a black hole, a measure of its information content, is proportional to the area of its event horizon, not its volume. This was a groundbreaking insight because it suggested that all the information about the matter and energy swallowed by a black hole could be encoded on its two-dimensional surface. Later, physicist Gerard T. Hooft and string theorist Leonard Susskind expanded on this idea, proposing that the entire universe might operate on a similar principle. According to the holographic principle, the three-dimensional world we perceive could be a projection of information stored on a distant two-dimensional boundary. So, what evidence supports this radical idea? One of the most compelling pieces comes from the study of quantum gravity, the quest to unify general relativity with quantum mechanics. These two frameworks are the backbone of modern physics, but they don't play well together. General relativity describes the universe on large scales, while quantum mechanics governs the tiny world of particles. The holographic principle offers a potential bridge between them by suggesting that gravity, and by extension, space and time, might emerge from quantum interactions on a lower dimensional surface. This idea has been supported by mathematical models, particularly in the context of string theory, where certain configurations of space-time can be described by equations that operate in fewer dimensions. But the implications of the holographic principle go far beyond theoretical math. If the universe is a two-dimensional projection, then the laws of physics we've come to rely on, gravity, electromagnetism, even the speed of light, might not be fundamental truths. Instead, they could be emergent properties arising from the way information is encoded and processed on the lower dimensional surface. This would mean that the rules governing our reality aren't fixed and absolute, but rather suggestions shaped by the underlying structure of the universe. It's a humbling thought, one that challenges the very foundation of how we understand existence. Imagine for a moment that you're watching a movie on a screen. The images appear three-dimensional, but you know they're just pixels arranged in a flat plane. The holographic principle suggests that our universe works in a similar way. The depth, the texture, the sense of space and time, all of it might be an illusion, a projection of information from a simpler, two-dimensional reality. This doesn't just change how we see the universe, it changes how we see ourselves. If the laws of physics are emergent rather than fundamental, then our understanding of reality is far more flexible and far more mysterious than we've ever imagined. And then there's the question of evidence. How could we ever test such a radical idea? One approach is to look for discrepancies in the way the universe behaves at very small scales or very high energies, where the holographic principle predicts subtle differences from the predictions of standard physics. Another is to study the cosmic microwave background radiation, the faint afterglow of the Big Bang, for patterns that might hint at a two-dimensional origin. While these experiments are still in their early stages, they represent the first steps toward probing one of the most profound ideas in modern science. The holographic principle isn't just a theory, it's a paradigm shift. It invites us to rethink everything we thought we knew about the universe, from the nature of space and time to the very meaning of reality. And as we continue to explore this idea, we're reminded that science is a journey of discovery, full of surprises and challenges. The holographic principle might not be the final answer, but it's a powerful reminder that the universe is far stranger, far more complex, and far more wondrous than we've ever dared to imagine. And in that strangeness lies the possibility that the laws of physics aren't set in stone. They're more like suggestions waiting to be rewritten by the next great discovery. Imagine two particles separated by billions of light years, yet somehow still connected. Change the state of one, and the other instantly responds, as if they're whispering secrets across the cosmos faster than the speed of light. This isn't science fiction, it's quantum entanglement, one of the most baffling and fascinating phenomena in all of physics. Dubbed spooky action at a distance by Einstein himself, entanglement defies everything we thought we knew about how the universe works. It challenges the very notion of local realism, the idea that objects are only influenced by their immediate surroundings, and suggests that reality might be far more interconnected than we ever imagined. At its core, entanglement is a relationship between particles that links their properties in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. Think of it like a pair of magical dice. Roll one, and the other will always show the same number, even if it's on the other side of the galaxy. This connection isn't just strange, it's profoundly counterintuitive. After all, according to Einstein's theory of relativity, nothing can travel faster than light. So how can entangled particles communicate instantaneously? The answer lies in the peculiar nature of quantum mechanics, where the rules of the game are very different from what we experience in our everyday lives. One of the key implications of entanglement is that it challenges the concept of local realism. Local realism assumes that objects have definite properties before they're measured and that no influence can travel faster than light. But entanglement suggests something far more radical, that particles don't have definite states until they're observed, and that their states are somehow linked across space and time. This idea was put to the test in the 1960s by physicist John Bell, who devised a set of experiments to determine whether particles really could influence each other instantaneously. The results were clear. Entanglement violates Bell's inequalities, meaning that local realism can't fully explain what's happening. Instead, it seems that the universe operates on a more holistic, interconnected level. This non-local behavior has profound implications for our understanding of reality. If entanglement is real, and countless experiments have confirmed that it is, then the universe isn't just a collection of separate objects following fixed rules. Instead, it's a deeply interconnected web where particles can influence each other across vast distances in ways that seem to defy the limits of space and time. It's as if the universe itself is a single, unified system with every part subtly connected to every other part. This doesn't just challenge our understanding of physics, it challenges our understanding of existence itself. But what does this mean for the laws of physics? If entanglement suggests that the universe is non-local, then the rules we've come to rely on might not be as universal as we thought. Instead, they could be more like guidelines, applicable in certain contexts but breaking down in others. This idea opens the door to a more flexible, dynamic understanding of reality, one where the laws of physics aren't set in stone but emerge from deeper, more fundamental processes. It's a humbling thought, one that reminds us how much we still have to learn about the cosmos. So, what's next for entanglement? Scientists are already exploring its potential applications, from quantum computing to secure communication. But beyond its practical uses, entanglement invites us to rethink our place in the universe. Are we truly separate beings, or are we all part of a larger, interconnected whole? As we continue to unravel the mysteries of quantum entanglement, we're reminded that the universe is far stranger, far more mysterious, and far more beautiful than we've ever imagined. And in that strangeness lies the possibility that the laws of physics might not be as rigid as we once believed. They could be mere suggestions, waiting to be rewritten by the next great discovery. What if the very act of observing the universe changes it? What if the laws of physics aren't just rules written in stone, but are influenced by something as elusive as consciousness itself? This idea might sound like something out of a philosophical debate, but it's a question that's been haunting the edges of quantum mechanics for decades. At the heart of this mystery is the observer effect, the notion that the act of measurement or observation can alter the outcome of a quantum experiment. It's a concept that blurs the line between the observer and the observed, suggesting that consciousness might play a far more significant role in shaping reality than we've ever imagined. The observer effect first came to light in the early days of quantum mechanics, most famously through the double-slit experiment. When particles like electrons are fired at a barrier with two slits, they create an interference pattern on the other side, behaving like waves. But here's the twist. When scientists try to observe which slit the electron passes through, the interference pattern disappears and the electrons start behaving like particles. It's as if the electrons know they're being watched, changing their behavior based on the presence of an observer. This phenomenon has led some to speculate that consciousness, the act of observation, might be influencing the outcome of these experiments. But what does it mean for consciousness to influence reality? Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that particles exist in a superposition of states, essentially all possible states at once, until they're observed. At that moment, the wave function collapses and the particle takes on a definite state. This idea implies that the observer isn't just a passive spectator, but an active participant in shaping reality. It's a radical notion, one that challenges the traditional view of physics as an objective science, entirely independent of the human mind. This idea becomes even more intriguing when we consider the role of the mind in quantum experiments. In the 1960s, physicist Eugene Wigner proposed a thought experiment now known as Wigner's friend. Imagine two observers, one inside a lab conducting a quantum experiment and another outside the lab. The observer inside measures the experiment and sees a definite outcome, but the observer outside, applying the rules of quantum mechanics, would describe the entire lab, including the first observer, as being in a superposition. Who's right? Does reality depend on who's observing it? Wigner suggested that consciousness might be the key to resolving this paradox, implying that the mind plays a fundamental role in determining what's real. Of course, this idea is far from universally accepted. Critics argue that equating consciousness with the observer effect is a leap too far. They point out that observation in quantum mechanics doesn't necessarily require a conscious observer. It could be any interaction with a measuring device. In this view, the collapse of the wave function is a physical process, not a mental one. But even if consciousness isn't directly causing the collapse, the fact that observation changes the outcome of experiments raises profound questions about the nature of reality. Are the laws of physics truly objective, or do they depend on how we interact with the universe? This debate has implications far beyond the lab. If consciousness does play a role in shaping reality, it could mean that the universe is far more dynamic and interactive than we've ever imagined. It might suggest that the laws of physics aren't fixed and universal, but are instead contingent on the presence of observers. This doesn't just challenge our understanding of science, it challenges our understanding of ourselves. Are we passive participants in a predetermined universe, or are we co-creators of reality, shaping the cosmos simply by observing it? And then there's the question of what consciousness actually is. Is it a product of the brain, as most scientists believe, or is it something more fundamental, a property of the universe itself? Some theories, like panpsychism, suggest that consciousness might be a basic feature of reality, present even at the level of particles. If that's true, then the observer effect might not be so much about human minds influencing the universe as it is about the universe itself being inherently conscious. These ideas are still speculative, but they invite us to think differently about the nature of reality. They remind us that science isn't just about discovering the laws of the universe, it's about understanding our place within it. If the laws of physics are influenced by consciousness, then the universe isn't just a cold, mechanical system. It's a living, evolving entity shaped in part by the minds that observe it. And as we continue to explore these profound questions, we're left with a sense of wonder, a reminder that reality might be far stranger, far more interconnected, and far more beautiful than we've ever dared to imagine. What if the universe we see is just the tip of the iceberg? What if, hidden from our view, there are other dimensions, realms where the laws of physics are entirely different from what we know? This isn't just a wild speculation. It's a serious proposal from some of the most advanced theories in physics. From the curled-up dimensions of string theory to the vast brains of M-theory, alternate dimensions could hold the key to understanding why our universe works the way it does and why it might not be the only one. Let's start with string theory, a framework that suggests the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. For this theory to work mathematically, it requires more than the 3 spatial dimensions we're familiar with. In fact, it needs at least 10 dimensions, 6 of which are compactified or curled up on scales so small we can't perceive them. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but up close, you can see it has a circular dimension wrapped around it. String theory's extra dimensions are like that, hidden from our everyday experience but potentially playing a crucial role in shaping the universe. But what if these extra dimensions aren't just mathematical curiosities? What if they're places where the laws of physics are completely different? In some versions of string theory, these compactified dimensions could host entirely unique sets of physical constants, things like the strength of gravity or the speed of light. This means that the rules we take for granted in our universe might not apply everywhere. Instead, they could be just one set of parameters among an infinite array of possibilities, each corresponding to a different configuration of these hidden dimensions. Then there's M-theory, an extension of string theory that introduces the idea of brains, short for membranes. These brains are like sheets floating in a higher dimensional space, and our universe could be one of them. According to this idea, the 3 dimensions we experience might be embedded in a much larger, multi-dimensional reality. Other brains could exist parallel to ours, each with its own set of physical laws. It's a staggering thought, entire universes separated by dimensions we can't perceive, each playing by its own rules. In this view, our universe isn't the center of everything, it's just one slice of a much larger cosmic pie. So, why does this matter? For one, these theories could help explain some of the biggest mysteries in physics. Take the fine-tuning problem, for example. The fundamental constants of nature, like the charge of an electron or the density of dark energy, seem to be precisely calibrated to allow for the existence of life. If these values were even slightly different, stars wouldn't form, atoms wouldn't hold together, and life as we know it would be impossible. But in a multi-dimensional universe, this fine-tuning isn't so mysterious. If there are countless dimensions with different physical laws, it's no surprise that at least one would have the right conditions for life. We just happen to live in that one. But these ideas don't just solve problems, they raise profound questions. If the laws of physics can vary from one dimension to another, what does that mean for the idea of universal truths? Are the laws we've discovered in our universe truly fundamental? Or are they just local rules that apply to our particular corner of reality? This challenges the very foundation of science, which has always sought to uncover universal principles that apply everywhere, always. If alternate dimensions exist, then those principles might not be as universal as we thought. And then there's the question of evidence. If other dimensions exist, how could we ever detect them? Some scientists have proposed looking for fingerprints of these dimensions in the behavior of particles or in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Others suggest that gravitational waves, ripples in space-time caused by violent cosmic events, might carry clues about the existence of higher dimensions. While these ideas are still speculative, they represent the first steps toward testing theories that, for now, remain largely theoretical. The idea of alternate dimensions doesn't just challenge our understanding of the universe, it invites us to think bigger. It reminds us that reality might be far more complex, far more diverse, and far more wondrous than we've ever imagined. Whether these dimensions are curled up, stretched out, or floating as brains in a higher dimensional space, they suggest that the universe is a place of infinite possibilities, where the laws of physics aren't set in stone but shaped by the unique conditions of each dimension. And as we continue to explore these ideas, we're left with a profound sense of wonder, a reminder that the universe might be far stranger, far more flexible, and far more beautiful than we've ever dared to imagine. What if the universe is playing a cosmic game of chance, and we've somehow drawn the winning hand? This is the essence of the fine-tuning problem, one of the most perplexing and profound questions in modern science. Why are the constants of nature, things like the strength of gravity, the mass of an electron, or the density of dark energy, so precisely calibrated to allow for life? It's as if the universe has been fine-tuned to an almost impossible degree, raising the question, is this a cosmic coincidence, or is there something deeper at work? Let's start with the basics. The constants of nature are the fixed values that govern how the universe operates. They're the numbers behind the equations, the speed of light, the charge of an electron, the force of gravity, and they're incredibly precise. If any of these values were even slightly different, the universe as we know it wouldn't exist. For example, if gravity were just a tiny bit stronger, stars would burn out too quickly, leaving no time for planets to form or life to evolve. If the electromagnetic force were weaker, atoms wouldn't hold together, and chemistry as we know it would be impossible. The list goes on, and the odds of all these constants aligning perfectly seem astronomically low. This startling precision has led some to suggest that the universe might have been designed with life in mind. It's a provocative idea, one that straddles the line between science and philosophy. But before we jump to conclusions, let's consider the alternatives. One possibility is the multiverse theory, which we've touched on earlier. If there are countless universes, each with its own set of physical constants, then it's no surprise that at least one would have the right conditions for life. In this view, our universe isn't special, it's just the one we happen to inhabit. It's like buying a lottery ticket. The odds of winning are slim, but if enough people play, someone's bound to hit the jackpot. But the multiverse theory isn't the only explanation. Some scientists argue that the fine-tuning problem might point to a deeper set of laws, a kind of metaphysics that governs the behavior of the constants themselves. Think of it like a game of chess. The rules of the game are fixed, but the way the pieces move is determined by a higher set of principles. In the same way, the constants of nature might not be arbitrary, but instead determined by a more fundamental framework that we're only beginning to uncover. This idea opens the door to a universe that's far more structured and far more mysterious than we've ever imagined. Of course, not everyone agrees. Some physicists argue that the fine-tuning problem might not be a problem at all. They suggest that our understanding of the universe is still incomplete, and what we see as fine-tuning might just be a result of our limited perspective. For example, if we discover new laws or principles that explain why the constants have the values they do, the fine-tuning problem might simply disappear. It's a reminder that science is a journey, and what seems like a mystery today might be solved tomorrow. Then there's the philosophical angle. The fine-tuning problem forces us to confront questions about the nature of existence and our place in the cosmos. If the universe is fine-tuned for life, does that mean life has a special significance? Or is it just a happy accident, a cosmic roll of the dice? These questions don't have easy answers, but they invite us to think more deeply about what it means to exist in a universe that seems so perfectly suited for us. At the same time, the fine-tuning problem raises fascinating questions about the nature of the laws of physics themselves. If the constants of nature are so precisely tuned, could they change over time? Could the laws of physics evolve as the universe itself evolves? This idea is still speculative, but it opens up a world of possibilities. Perhaps the universe isn't a static entity governed by rigid rules, but a dynamic, evolving system, constantly adjusting to create the conditions necessary for life. Ultimately, the fine-tuning problem reminds us that the universe is far more mysterious and complex than we've ever imagined. It doesn't just challenge our understanding of physics, it challenges our understanding of ourselves. Are we the result of a cosmic accident, or is there something more at work? As we continue to explore these questions, we're left with a profound sense of wonder, a reminder that the universe is not just a place we inhabit, but a story we're still learning to read. And in that story, the laws of physics might not be the final word, they might just be the beginning. What if the rules governing our universe aren't written in stone, but are instead the result of something far more dynamic? Imagine a kaleidoscope. Its intricate patterns aren't predetermined but emerge from the way light interacts with the mirrors and colored glass inside. In a similar way, some scientists propose that the laws of physics might not be fundamental truths but rather emergent properties, arising from the complexity of the universe itself. This idea, known as emergent laws, challenges our traditional view of physics and opens the door to a universe that's far more fluid and interconnected than we've ever imagined. To understand this concept, let's start with something familiar: water. At room temperature, water behaves predictably. It flows, fills containers, and forms droplets. But when you lower the temperature, something remarkable happens. The water molecules slow down, rearrange themselves, and suddenly you have ice. This transition from liquid to solid is an example of a phase transition, a process where a system undergoes a sudden change in its properties. What's fascinating is that the rules governing ice aren't written into the individual water molecules themselves. They emerge from the collective behavior of countless molecules interacting in just the right way. In other words, the laws of ice aren't fundamental, they're the result of complexity. Now, let's scale this idea up to the cosmos. Just as water molecules organize themselves into ice, could the fundamental laws of physics emerge from the interactions of more basic components? Some physicists think so. Take gravity, for example. According to Einstein's general relativity, gravity is the result of massive objects warping the fabric of space-time. But what if space-time itself is emergent? What if it's not a fundamental entity but something that arises from the collective behavior of underlying quantum particles? This idea, known as emergent gravity, suggests that the rules we've come to rely on, like the inverse square law, might not be absolute but rather the result of how space-time organizes itself on large scales. This concept becomes even more intriguing when we consider self-organization, a phenomenon where systems spontaneously arrange themselves into ordered structures without any external guidance. Think of a flock of birds. Each bird follows simple rules like staying close to its neighbors, but the flock as a whole exhibits complex, coordinated behavior. In the same way, the laws of physics might emerge from the interactions of simpler components like quantum fields or strings organizing themselves into the patterns we observe. This would mean that the laws we see aren't dictated by some external force, but are instead the natural outcome of how the universe evolves. So, what does this mean for our understanding of reality? If the laws of physics are emergent, then they might not be universal truths, but rather local phenomena, shaped by the specific conditions of our universe. This idea has profound implications. For one, it suggests that the rules we've discovered might not apply everywhere. In a different universe, or even in a different region of our own, the laws of physics could be entirely different, emerging from a unique set of interactions. It's a humbling thought, one that reminds us how much we still have to learn about the cosmos. But emergent laws also raise fascinating questions about the nature of science itself. If the laws of physics aren't fixed and immutable, but instead arise from complexity, does that mean they can change over time? Could the universe evolve in ways that alter its fundamental rules? Some theories suggest that this might be possible, particularly in the extreme conditions of the early universe or near black holes. In these environments, the familiar laws of physics might break down, giving way to new, emergent rules that we're only beginning to understand. This idea also invites us to think differently about the relationship between simplicity and complexity. In our quest to uncover the fundamental laws of the universe, we've often looked for the simplest, most elegant explanations. But what if complexity itself is the key? What if the richness of the universe, its galaxies, stars, and even life, isn't the result of simple rules but emerges from the intricate interplay of countless components? This perspective shifts the focus from finding the ultimate building blocks of reality to understanding how those building blocks organize themselves into the world we see. As we explore the idea of emergent laws, we're reminded that the universe is a place of infinite possibilities, where the rules we've come to rely on might just be the tip of the iceberg. Whether it's the behavior of water molecules or the structure of space-time, the laws of physics might not be handed down from on high. They could be the result of a cosmic dance shaped by the interactions of the universe itself. And as we continue to unravel these mysteries, we're left with a profound sense of wonder, a reminder that reality might be far more flexible, far more dynamic, and far more beautiful than we've ever imagined. Mathematics is often called the language of the universe, a tool so precise and powerful that it allows us to describe everything from the motion of planets to the behavior of particles. But here's a thought that might make you pause. What if mathematics isn't something we've discovered about the universe, but something we've invented? What if the elegant equations and formulas we use to describe reality aren't universal truths but constructs of the human mind? This isn't just a philosophical musing, it's a debate that cuts to the heart of how we understand the laws of physics and their role in shaping reality. On one side of the debate are the mathematical Platonists, who argue that mathematics exists independently of human thought. To them, numbers, equations, and geometric shapes are like distant stars always there, waiting to be discovered. When we find a mathematical truth, we're uncovering something that has always existed, even if we didn't know it yet. This view suggests that the laws of physics are universal and unchanging, woven into the very fabric of reality. It's a comforting idea, one that aligns with our instinct to see order and structure in the cosmos. But then there's the opposing view, mathematical constructivism. This perspective argues that mathematics is a human invention, a language we've created to make sense of the world. In this view, the laws of physics aren't pre-existing truths but frameworks we've built to describe patterns we observe. Think of it like a map. A map isn't the territory itself, but a useful tool for navigating it. Similarly, mathematics might not be the true language of the universe. It's just the best tool we've developed so far. This debate isn't just academic. It has profound implications for how we see the laws of physics. If mathematics is a human invention, then the laws we've derived from it might not be absolute. They could be shaped by the way we perceive and interpret the universe, rather than being intrinsic to reality itself. It's a humbling thought. The rules we've come to rely on, gravity, electromagnetism, even the speed of light, might not be universal truths but rather approximations, tailored to our particular way of understanding the world. Consider, for example, how different cultures throughout history have developed their own mathematical systems. The ancient Greeks, with their love of geometry, saw the world in terms of perfect shapes and ratios. The Mayans, on the other hand, used a base 20-number system and had a sophisticated understanding of astronomy. These systems weren't wrong, they were simply different ways of interpreting the same reality. If mathematics is a tool we've invented, then it's possible that the laws of physics aren't fixed but are instead shaped by the mathematical frameworks we choose to use. This idea becomes even more intriguing when we consider how mathematics evolves. Over time, new branches of math have emerged to describe phenomena that were previously incomprehensible. Calculus, for instance, was developed to explain motion and change, while complex numbers were introduced to solve equations that had no real number solutions. Each new development expanded our ability to describe the universe, but it also raised questions. Are we uncovering deeper truths, or are we simply refining our tools to better fit what we observe? And then there's the question of beauty. Many physicists are drawn to elegant mathematical formulations, believing that simplicity and symmetry are signs of truth. But what if our preference for beauty is a reflection of our own biases rather than an indicator of universal laws? Could it be that the universe is far messier and more chaotic than our mathematical models suggest, and that our search for elegance is leading us astray? This isn't to say that mathematics isn't useful, it clearly is, but it does challenge the idea that the laws of physics are as fixed and absolute as we've been led to believe. So, where does this leave us? If mathematics is a human invention, then the laws of physics might not be the final word on reality. Instead, they could be more like guidelines shaped by the way we perceive and interpret the universe. This doesn't diminish the power of science. It simply reminds us that our understanding is always evolving, always incomplete. As we continue to explore the cosmos, we're left with a profound sense of wonder, a reminder that the universe might be far more complex, far more dynamic, and far more mysterious than we've ever imagined. And in that mystery lies the possibility that the laws of physics aren't set in stone, they're more like suggestions, waiting to be rewritten by the next great discovery. What if the universe has secrets it refuses to share? For all the incredible progress we've made in understanding the cosmos, there are still fundamental limits to what we can know. These boundaries aren't just gaps in our knowledge, they're hard limits built into the fabric of reality itself. From the uncertainty principle to the cosmic horizon, the universe seems to have a way of keeping some things just out of reach. And as we push against these boundaries, we're forced to confront a startling possibility. The laws of physics we've uncovered might not be the full story. They could be glimpses of a deeper, more elusive reality, one that's far more complex and mysterious than we've ever imagined. Let's start with the uncertainty principle, one of the cornerstones of quantum mechanics. This principle tells us that there's a fundamental limit to how much we can know about a particle's properties. For example, the more precisely we measure a particle's position, the less we can know about its momentum, and vice versa. It's not that our tools aren't good enough, it's a fundamental property of the universe. This uncertainty isn't just a quirk of quantum mechanics, it's a profound statement about the nature of reality. At the smallest scales, the universe is inherently fuzzy, governed not by rigid laws but by probabilities. This challenges the very idea of a deterministic universe where everything follows predictable cause and effect rules. Instead, it suggests that at its core, reality is built on uncertainty. But the limits of scientific knowledge don't stop at the quantum level. Consider the cosmic horizon, the boundary beyond which we can't see. Because the universe is expanding, there are regions of space so distant that their light hasn't had time to reach us. This means there's a limit to how far we can observe, and thus, how much of the universe we can ever know. It's like standing on a beach and trying to see the entire ocean. No matter how powerful your telescope, there will always be a horizon you can't cross. This cosmic horizon isn't just a practical limitation. It's a reminder that the universe is far larger and more complex than our ability to comprehend it. Then there's the problem of complexity. As we delve deeper into the mysteries of the universe, we're finding that the systems we study, from the behavior of particles to the structure of galaxies, are becoming increasingly complex. This complexity isn't just a challenge for our tools and theories. It's a fundamental limit to what we can predict and understand. Take weather systems, for example. Even with supercomputers and vast amounts of data, we can't predict the weather with perfect accuracy more than a few days in advance. The same principle applies to the cosmos. The more we learn, the more we realize how much we don't know. So, what do these limits mean for our understanding of the laws of physics? If there are fundamental boundaries to what we can observe and predict, does that mean the laws we've discovered are incomplete or even illusory? Some scientists argue that the laws of physics aren't universal truths but rather approximations, useful within certain contexts but breaking down when we push them to their limits. It's like using a map to navigate a city. The map is helpful, but it's not the territory itself. In the same way, the laws of physics might be tools we've developed to make sense of the universe, rather than the ultimate truths we've often assumed them to be. This doesn't mean that science is futile or that the laws of physics are meaningless. On the contrary, these limits remind us of the incredible complexity and beauty of the universe. They challenge us to think differently, to embrace uncertainty, and to remain open to new ideas. They also remind us that science is a journey, not a destination, a process of exploration and discovery that's always evolving. As we continue to push against the boundaries of scientific knowledge, we're left with a profound sense of wonder. The universe is far stranger, far more mysterious, and far more wondrous than we've ever imagined. And in that mystery lies the possibility that the laws of physics aren't set in stone. They're more like signposts, pointing us toward a deeper understanding of reality. The question is, are we ready to embrace a universe where not everything can be known, and where the journey of discovery is as important as the answers we find? Imagine trying to understand the universe with nothing but your eyes and a few rudimentary tools. For centuries, that's exactly what scientists did, peering into the night sky and pondering the mysteries of the cosmos. But as our tools evolved, so did our understanding. From the invention of the telescope to the development of particle accelerators, technology has been the driving force behind some of the most profound discoveries in physics. It's not just that these tools allow us to see further or probe deeper. They fundamentally change how we think about the universe. They reveal layers of reality we never knew existed, challenging our assumptions and reshaping our understanding of the laws that govern everything. Let's start with one of the most iconic pieces of scientific technology, the telescope. When Galileo first turned his telescope to the heavens in 1609, he didn't just see more stars. He saw a universe that was far more complex than anyone had imagined. The discovery of Jupiter's moons, the phases of Venus, and the rugged surface of our own moon shattered the medieval view of a perfect, unchanging cosmos. It was a revelation that set the stage for the scientific revolution, proving that the universe wasn't just a backdrop for human drama, but a dynamic, ever-changing system governed by laws we could begin to understand. Without the telescope, we might still be thinking of the Earth as the center of the universe. Fast forward to the 20th century, and the tools of discovery became even more extraordinary. Take particle accelerators, for example. These massive machines, like the Large Hadron Collider, are designed to smash particles together at nearly the speed of light, recreating conditions that haven't existed since the earliest moments of the Big Bang. In 2012, the LHC made headlines with the discovery of the Higgs boson, a particle that helps explain why other particles have mass. This wasn't just a new piece of the puzzle. It was a cornerstone of the Standard Model of particle physics, a theory that describes the fundamental building blocks of the universe. Without particle accelerators, we'd still be guessing about the nature of matter itself. But it's not just about discovering new particles or observing distant stars. Technology also helps us test the limits of our understanding. Consider gravitational wave detectors like LIGO and Virgo. These incredibly sensitive instruments are designed to detect ripples in space-time caused by cataclysmic events like the collision of black holes or neutron stars. When LIGO made its first detection in 2015, it wasn't just a triumph of engineering, it was a confirmation of Einstein's century-old prediction about the nature of gravity. It showed that space-time isn't a static stage but a dynamic, flexible fabric that can stretch and ripple like the surface of a pond. This discovery didn't just validate a theory, it opened up a whole new way of observing the universe, one that doesn't rely on light but on the very fabric of reality itself. And then there's the role of computational technology. The universe is unimaginably complex, and solving the equations that describe it often requires more than just pen and paper. Modern supercomputers allow us to simulate everything from the formation of galaxies to the behavior of quarks, giving us insights that would be impossible to achieve through observation alone. These simulations don't just help us understand the universe, they also help us test our theories, revealing where they might break down or where new physics might be hiding. In a sense, technology has become a laboratory for the mind, allowing us to explore ideas that would otherwise remain purely theoretical. But here's the thing, every time we build a new tool or develop a new technique, we're reminded of how much we don't know. The universe has a way of surprising us, revealing phenomena that defy our expectations and challenge our understanding. For every question we answer, a dozen more seem to appear. And that's the beauty of science. It's not about arriving at a final answer, but about the journey of discovery itself. Technology doesn't just give us answers, it gives us new questions, pushing us to think bigger, dig deeper, and imagine farther. So, what does this mean for the laws of physics? If our understanding is shaped by the tools we use, then the laws we've discovered might not be the ultimate truths, but rather the best descriptions we have right now. They're not set in stone, they're evolving, just like our technology. And as we continue to push the boundaries of what's possible, we're left with a profound sense of wonder. The universe is far more complex, far more mysterious, and far more beautiful than we've ever imagined. And with every new discovery, we're reminded that the journey is far from over, it's just getting started. Physics is often seen as a realm of cold, hard facts, a world of equations and experiments where there's little room for ambiguity. But beneath the surface of every formula and every discovery lies a deeper, more philosophical layer. What is reality, truly? How do we define it, and does our perception shape it? These aren't just abstract musings, they're questions that cut to the heart of what physics is trying to uncover. And as we explore them, we begin to see that the laws of physics might not be as rigid as they appear. Instead, they could be more like windows into a reality that's far more fluid and mysterious than we've ever imagined. Let's start with the nature of reality itself. At its core, physics is an attempt to describe how the universe works, but what does it mean to work? Are the laws we've discovered fundamental truths, or are they simply the best descriptions we've come up with so far? This question isn't new. It dates back to ancient philosophers like Plato and Aristotle, who debated whether the world we perceive is the real world or just a shadow of something deeper. Today, physicists like Carlo Rovelli echo this idea, suggesting that reality might not be made of objects at all, but of relationships and interactions. In this view, the laws of physics aren't absolute. They're patterns that emerge from the way things connect and interact. It's a shift in perspective that challenges the very foundation of how we see the universe. Then there's the role of the observer, a concept that's become central to quantum mechanics. The double-slit experiment, for example, shows that particles behave differently when they're being observed. This has led some to argue that consciousness itself might play a role in shaping reality. It's a controversial idea, one that blurs the line between the observer and the observed. But whether or not consciousness is directly influencing the outcome, the fact remains, the act of observation changes the system being observed. This suggests that the universe isn't a passive backdrop but an active, dynamic system that responds to how we interact with it. And if that's true, then the laws of physics might not be fixed rules but flexible guidelines, shaped in part by our presence within the cosmos. But what about the idea of determinism, the notion that every event is the inevitable result of what came before? For centuries, this idea dominated physics, from Newton's clockwork universe to Laplace's demon, a hypothetical being that could predict the future if it knew the position and momentum of every particle. But quantum mechanics threw a wrench into this view, introducing uncertainty and randomness at the most fundamental level. Suddenly, the universe wasn't a predictable machine but a place where chance plays a key role. This shift has profound philosophical implications. If the universe isn't deterministic, then the laws of physics might not be as rigid as we once thought. Instead, they could be probabilistic, offering a range of possible outcomes rather than a single, fixed result. And then there's the question of time. In our everyday lives, time feels like a steady, unyielding force flowing from past to future. But physics tells a different story. According to Einstein's theory of relativity, time isn't absolute. It's relative, stretching and bending depending on how fast you're moving or how strong gravity is. This challenges our intuitive sense of time as a linear, unchanging dimension. It suggests that the laws of physics might not be tied to a single, universal timeline, but could vary depending on the observer's perspective. This idea opens the door to a more flexible understanding of reality, one where the laws we've discovered might be just one of many possible frameworks. So, what does all this mean for the laws of physics? If reality is shaped by relationships, if observation changes the system being observed, if chance plays a role, and if time is relative, then the laws we've come to rely on might not be as absolute as we once believed. Instead, they could be emergent properties shaped by the conditions of the universe and the way we interact with it. This doesn't diminish the power of physics. It simply reminds us that science is a journey, not a destination. It's an ongoing exploration of a reality that's far more complex, far more dynamic, and far more wondrous than we've ever imagined. As we grapple with these philosophical questions, we're reminded that physics isn't just about discovering the laws of the universe, it's about understanding our place within it. It's a reminder that the cosmos isn't just a collection of particles and forces, but a living, evolving system, full of surprises and mysteries waiting to be uncovered. And as we continue to explore these profound questions, we're left with a sense of wonder, a reminder that reality might be far more flexible, far more interconnected, and far more beautiful than we've ever dared to imagine. What if the next great leap in physics is just around the corner? What if the tools and theories we're developing today could unlock secrets about the universe that we can barely imagine? The future of physics isn't just about refining what we already know. It's about venturing into uncharted territory where the rules might not be the same as the ones we've grown accustomed to. From the mind-bending potential of quantum computing to the cosmic whispers captured by gravitational wave detectors, the next chapter of physics promises to be as revolutionary as the discoveries of Newton, Einstein, and Planck. So, what's on the horizon, and how might these advancements change everything we think we know about the universe? Let's start with quantum computing, a field that's not just transforming technology, but also challenging our understanding of reality itself. Unlike classical computers, which process information in binary bits, zeros and ones, quantum computers use qubits, which can exist in multiple states simultaneously thanks to the principle of superposition. This means a quantum computer can explore countless possibilities at once, solving problems that would take classical computers millions of years in a matter of seconds. But here's where it gets fascinating. Quantum computers don't just crunch numbers faster, they operate in a realm where the rules of quantum mechanics reign supreme. This opens the door to simulating quantum systems, like the behavior of particles in a black hole or the early moments of the Big Bang, in ways that were previously impossible. By harnessing the power of quantum computing, we might finally crack some of the universe's most stubborn mysteries, from the nature of dark matter to the unification of quantum mechanics and gravity. Then there's gravitational wave astronomy, a field that's only just begun to reveal its potential. Since the first detection of gravitational waves in 2015, scientists have been using these ripples in space-time to observe some of the most violent and energetic events in the cosmos, colliding black holes, merging neutron stars, and even the faint echoes of the Big Bang itself. But this is just the beginning. Future observatories like the Laser Interferometer Space Antenna LISA will be sensitive enough to detect gravitational waves from the earliest moments of the universe, offering a glimpse into a time before stars, galaxies, or even light itself existed. These waves could carry clues about the nature of gravity, the existence of extra dimensions, and even the possibility of parallel universes. It's like listening to the universe's deepest secrets whispered across billions of years. But it's not just about building bigger and better tools, it's also about rethinking the fundamental frameworks of physics. Take string theory, for example. While it's still a work in progress, it offers a tantalizing possibility that all the forces and particles we observe are manifestations of tiny, vibrating strings. If proven, this theory could unify the four fundamental forces of nature into a single, elegant framework. Similarly, loop quantum gravity proposes that space-time itself is made up of discrete, quantized loops, challenging our traditional view of a smooth, continuous fabric. These theories are still speculative, but they represent bold attempts to push the boundaries of our understanding, suggesting that the laws of physics might not be as fixed as we once thought. And let's not forget the role of artificial intelligence in shaping the future of physics. AI isn't just a tool for crunching data, it's becoming a partner in discovery. Machine learning algorithms are helping physicists analyze vast datasets, from particle collisions at the Large Hadron Collider to the cosmic microwave background radiation. These algorithms can spot patterns and anomalies that human eyes might miss, leading to unexpected breakthroughs. In some cases, AI is even being used to propose new theories or design experiments, acting as a kind of digital co-pilot in the quest to understand the universe. So, what does all this mean for the laws of physics? If history is any guide, the future will likely bring surprises, discoveries that challenge our assumptions and force us to rethink what we thought we knew. The laws of physics might not be universal truths, but rather evolving frameworks, shaped by the tools and technologies we use to explore the cosmos. They might not be rigid rules, but flexible guidelines, adapting as we uncover new layers of reality. As we stand on the brink of these new frontiers, one thing is clear: the journey of discovery is far from over. The universe is a place of infinite possibilities, full of mysteries waiting to be uncovered. And as we continue to push the boundaries of what's possible, we're reminded that science isn't just about finding answers, it's about asking better questions. The future of physics isn't just about understanding the universe. It's about embracing the wonder of the unknown and the thrill of discovery. And in that journey, we might just find that the laws of physics aren't set in stone. They're more like suggestions waiting to be rewritten by the next great breakthrough. Imagination has always been the unsung hero of physics, the quiet force behind some of the most groundbreaking discoveries in human history. Think about it. long before telescopes peered into the depths of space or particle accelerators smashed atoms. It was the power of imagination that allowed scientists to dream beyond the visible, to ask questions that seemed impossible to answer. Albert Einstein famously relied on thought experiments like imagining riding a beam of light to develop his theory of relativity. These weren't just flights of fancy. They were deliberate, creative exercises that allowed him to break free from the constraints of conventional thinking and see the universe in a whole new way. And he wasn't alone. From Newton's apple to Schrödinger's cat, imagination has been the spark that ignites scientific revolutions. But what does imagination have to do with the laws of physics? At first glance, physics seems like a rigid discipline governed by equations and experiments where creativity might feel out of place. Yet, the truth is that imagination is the bridge between what we know and what we don't. It's what allows us to question the status quo, to wonder if the rules we've always relied on might be more like guidelines than absolute truths. For instance, take the concept of dark matter. We can't see it, touch it, or directly detect it, yet its gravitational effects are undeniable. Imagining what it might be, whether it's a new kind of particle or something even stranger, is the first step toward uncovering its secrets. Without imagination, we'd be stuck staring at the same equations, never daring to push beyond them. And then there's the realm of radical theories where imagination truly takes center stage. Consider string theory, which proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. This idea didn't come from crunching numbers or running experiments. It came from imagining a universe where the familiar rules of physics might not apply. Similarly, the multiverse theory, which suggests our universe might be just one of many, is a product of creative thinking, of asking, what if? These ideas might sound like science fiction, but they're rooted in rigorous mathematical frameworks. They're not wild guesses, they're bold, imaginative leaps that challenge us to rethink everything we thought we knew. But imagination isn't just about dreaming up new theories, it's also about how we test them. Take the concept of wormholes, for example. These hypothetical tunnels through space-time are a staple of sci-fi, but they're also a serious area of research in physics. Imagining what a wormhole might look like, how it could form, and what laws it might obey helps scientists design experiments and thought experiments to explore their plausibility. It's a reminder that imagination isn't just about asking questions, it's about finding ways to answer them, even when the answers seem out of reach. So why does imagination matter so much in physics? Because it's the tool that allows us to confront the unknown, to explore ideas that might seem impossible at first glance. It's what drives us to ask not just what is, but what could be. And in a universe as vast and mysterious as ours, that's exactly the kind of thinking we need. Whether it's pondering the nature of time, the origins of the cosmos, or the possibility of alternate dimensions, imagination is the key that unlocks new ways of seeing the world. But here's the thing, imagination doesn't work in isolation. It's not just about dreaming up wild ideas, it's about grounding those ideas in evidence, in the rigorous testing and experimentation that separates science from speculation. That's what makes physics so unique. It's a dance between creativity and discipline, between bold ideas and careful verification. And in that dance, we find the potential for discovery, for uncovering truths that might have remained hidden if we'd been too afraid to imagine. As we continue to explore the mysteries of the universe, one thing is clear. Imagination isn't just a luxury, it's a necessity. It's what allows us to push the boundaries of our understanding, to challenge the rules we thought were unbreakable, and to uncover the deeper truths that lie just beyond our reach. And in that process, we're reminded that the laws of physics might not be as rigid as we once believed. They could be more like suggestions waiting to be rewritten by the next great leap of imagination. What happens when science pushes the boundaries of what we think is possible? When radical theories emerge, challenging everything from the nature of reality to the very laws of physics, they don't just spark intellectual debates, they raise profound ethical questions. Should we pursue these ideas even if they upend our understanding of the universe? And if so, what are the risks and responsibilities that come with such exploration? This isn't just about curiosity, it's about the impact these discoveries could have on society, technology, and even our sense of identity. The ethics of radical theories aren't just a side note, they're at the heart of how we navigate the future of science. Let's start with the potential benefits. Radical theories often lead to breakthroughs that transform our world. Take quantum mechanics, for example. When it first emerged in the early 20th century, it was seen as bizarre, even heretical. Yet without it, we wouldn't have the technology that powers modern life, everything from smartphones to MRI machines. Similarly, the pursuit of radical ideas like string theory or the multiverse hypothesis could unlock entirely new ways of understanding the cosmos, potentially leading to technologies we can't yet imagine. These aren't just abstract concepts, they're pathways to progress, offering solutions to challenges in energy, medicine, and beyond. The ethical argument here is clear. By pushing the boundaries of science, we open doors to a better future. But with great potential comes great responsibility. Radical theories often challenge deeply held beliefs, not just in science but in philosophy, religion, and culture. For instance, the idea that our universe might be one of many in a vast multiverse could fundamentally alter how we see our place in existence. Is it ethical to pursue theories that might unsettle or even alienate people? And what about the risks? Some radical ideas, like certain applications of artificial intelligence or advanced genetic engineering, carry the potential for misuse. The same breakthroughs that could cure diseases or solve energy crises might also be weaponized or exploited. These aren't hypothetical concerns, they're real dilemmas that scientists and policymakers must grapple with as they decide which paths to pursue. This brings us to the question of who gets to decide. Scientific research isn't conducted in a vacuum. It's shaped by funding, priorities, and the values of those in power. Should a small group of experts determine the direction of radical research, or should the broader public have a say? For example, experiments involving particle accelerators or space exploration often come with hefty price tags. Is it ethical to invest billions in these projects when there are pressing social issues like poverty or climate change? These are complex questions with no easy answers, but they highlight the need for transparency and inclusivity in how scientific priorities are set. After all, the pursuit of knowledge isn't just about discovery, it's about ensuring that the benefits and risks are shared equitably. And then there's the question of unintended consequences. History is full of examples where scientific breakthroughs had effects that no one could have predicted. The development of nuclear energy, for instance, brought both clean power and the threat of catastrophic weapons. Similarly, radical theories in physics could lead to technologies that reshape society in ways we can't yet foresee. How do we prepare for these possibilities? One approach is to embrace a principle of precaution, carefully weighing the potential risks before diving headfirst into new frontiers. But this has its own challenges. Too much caution could stifle innovation, leaving us unprepared for future challenges. Striking the right balance is a delicate act, one that requires ongoing dialogue between scientists, policymakers, and the public. At its core, the ethics of radical theories remind us that science isn't just about answering questions, it's about asking the right ones. It's about understanding not only what we can do, but also what we should do. The pursuit of knowledge is a deeply human endeavor, shaped by our values, fears, and aspirations. And as we continue to explore the mysteries of the universe, we're reminded that the laws of physics aren't just scientific truths, they're ethical ones too. They challenge us to think not only about how the universe works, but also about how we want to live within it. And in that challenge lies the true beauty of science, its ability to inspire us, to push us forward, and to remind us of our shared responsibility to shape the future wisely. Physics doesn't exist in a vacuum, it thrives on collaboration, drawing inspiration and insight from a wide range of disciplines. From the precision of mathematics to the creativity of art and the deep questions posed by philosophy, the boundaries between fields are often where the most groundbreaking ideas are born. By uniting these diverse perspectives, scientists and thinkers have been able to challenge long-held assumptions about the universe, including the very notion that the laws of physics are fixed and unchanging. Instead, they suggest that these laws might be shaped by a broader, more interconnected context, one that's as rich and dynamic as the disciplines that contribute to it. Take mathematics, for example. It's often said that math is the language of physics, and for good reason. Equations and formulas are the tools physicists use to describe the universe, from the motion of planets to the behavior of particles. But math isn't just a passive tool, it's an active partner in discovery. Sometimes mathematicians uncover structures or patterns that physicists hadn't even considered, leading to entirely new ways of thinking about reality. For instance, the development of non-Euclidean geometry in the 19th century laid the groundwork for Einstein's theory of general relativity, reshaping our understanding of gravity. This kind of cross-pollination shows that the laws of physics aren't just waiting to be discovered, they're shaped by the frameworks we use to explore them. But collaboration doesn't stop at math. Philosophy, with its focus on fundamental questions about existence, knowledge, and reality, plays a crucial role in shaping how we interpret the discoveries of physics. Consider the concept of time. Physicists can describe how time behaves, how it slows down near massive objects or speeds up at high velocities, but it's philosophers who ask what time is. Is it a fundamental feature of the universe, or is it something that emerges from deeper processes? These questions aren't just abstract musings. They challenge physicists to think beyond their equations and consider the broader implications of their work. In this way, philosophy acts as a kind of compass, guiding scientific exploration toward questions that might otherwise go unasked. And then there's art, which might seem like an unlikely partner for physics at first glance. Yet, art and science share a common goal: to make sense of the world and express that understanding in meaningful ways. Artists often draw inspiration from scientific concepts, using them to create works that explore the beauty and complexity of the universe. But the influence goes both ways. The creative, intuitive thinking that artists use can inspire scientists to approach problems in new ways. For example, the abstract shapes and patterns found in modern art have influenced the way some physicists think about symmetry and structure in the universe. This interplay between art and science reminds us that the laws of physics aren't just cold, hard facts, they're part of a larger tapestry of human creativity and curiosity. What's fascinating about these interdisciplinary collaborations is how they challenge the idea of fixed, unchanging laws. When physicists work with mathematicians, philosophers, and artists, they're not just refining existing theories, they're reimagining what those theories could be. They're asking questions like, could the laws of physics change over time? Are they universal, or do they vary in different contexts? These questions don't just push the boundaries of science, they open up entirely new ways of thinking about the universe. This collaborative approach also highlights the importance of context. The laws of physics might not be absolute truths, but rather emergent properties, shaped by the conditions of the universe and the frameworks we use to understand it. For example, the rules that govern the behavior of particles at the quantum level are very different from those that apply to everyday objects. This suggests that the laws of physics aren't set in stone, they're context-dependent, emerging from the complexity of the systems they describe. By bringing together different disciplines, we gain a richer, more nuanced understanding of reality. Collaboration doesn't just solve problems, it creates new possibilities, challenging us to think bigger and dig deeper. It reminds us that science isn't just about finding answers, it's about asking better questions. And as we continue to explore the mysteries of the universe, one thing is clear: the laws of physics aren't just rules to be followed, they're invitations to explore, to create, and to imagine. And in that exploration, we might just find that the universe is far more flexible, far more interconnected, and far more wondrous than we've ever dared to imagine. What if failure isn't the end of the road, but the very path to discovery? In science, and especially in physics, failure isn't just a possibility, it's a necessity. Every misstep, every experiment that doesn't go as planned, and every theory that gets disproven is a stepping stone toward a deeper understanding of the universe. It's through these failures that we uncover the limits of our knowledge, challenge our assumptions, and ultimately push the boundaries of what we thought was possible. Far from being a setback, failure is the engine that drives scientific progress, reminding us that the laws of physics aren't set in stone. They're constantly evolving, shaped by what we learn when things don't go as expected. Consider the story of the Michelson-Morley experiment conducted in the late 19th century. At the time, scientists believed that light traveled through an invisible medium called the luminiferous ether, which permeated the universe. Michelson and Morley set out to detect this ether by measuring the speed of light in different directions. But no matter how precise their equipment or how carefully they conducted their experiments, they kept coming up empty-handed. Instead of confirming the existence of the ether, their results suggested it didn't exist at all. This failure wasn't just a disappointment, it was a revolution. It paved the way for Einstein's theory of relativity, which completely redefined our understanding of space, time, and the very nature of light. What seemed like a failed experiment turned out to be one of the most important discoveries in the history of physics. But failure doesn't always lead to immediate breakthroughs. Sometimes it's a slow, painstaking process of trial and error. Take the search for a unified theory of physics, for example. For decades, scientists have been trying to reconcile the two great pillars of modern physics, quantum mechanics and general relativity, into a single, coherent framework. Despite countless attempts, no one has succeeded yet. Theories like string theory and loop quantum gravity have shown promise, but they've also run into dead ends and unresolved problems. These setbacks might seem frustrating, but they're also invaluable. Each failed attempt teaches us something new, helping us refine our questions and inch closer to the answers. It's a reminder that science isn't about finding the right answer right away. It's about learning how to ask better questions. And then there's the role of failure in challenging our assumptions. One of the most powerful ways science progresses is by proving itself wrong. When a theory is disproven, it forces us to rethink our understanding of the universe and consider new possibilities. For instance, the discovery of dark energy in the late 1990s was a result of failed expectations. Astronomers had assumed that the expansion of the universe was slowing down due to gravity, but their observations showed the opposite: the expansion was accelerating. This unexpected result didn't just overturn a key assumption in cosmology. It opened up a whole new field of study, revealing that the universe is far more mysterious than we ever imagined. Failure also highlights the limits of our knowledge. When experiments don't yield the expected results, it's often a sign that we're missing something, a hidden variable, a flawed assumption, or even a completely new phenomenon. Take the case of the Large Hadron Collider, which was designed to probe the fundamental nature of matter. While it successfully discovered the Higgs boson, it also failed to find evidence of supersymmetry, a theory that many physicists had hoped would explain some of the universe's deepest mysteries. This failure didn't mean the end of the road. Instead, it pushed scientists to explore alternative explanations and consider new possibilities. It's a reminder that the universe doesn't always conform to our expectations, and that's where the real discoveries happen. What's fascinating about failure is how it reveals the dynamic nature of the laws of physics. When a theory is disproven or an experiment fails, it doesn't mean we've hit a wall, it means we've found a crack in our understanding, a place where the rules we thought were fixed might actually be more flexible. For example, the failure of classical physics to explain the behavior of particles at the quantum level led to the development of quantum mechanics, a framework that completely redefined how we think about reality. This evolution of our understanding shows that the laws of physics aren't immutable truths, they're working models, constantly being refined and updated as we learn more about the universe. So, what does all this mean for the future of physics? It means that failure isn't something to fear, it's something to embrace. Every failed experiment, every disproven theory, and every unanswered question is an opportunity to push the boundaries of our understanding. It's through these failures that we discover the gaps in our knowledge, challenge our assumptions, and ultimately uncover the deeper truths that lie just beyond our reach. And as we continue to explore the mysteries of the universe, one thing is clear. The laws of physics aren't fixed and unchanging, they're a living, evolving framework shaped by our successes and, just as importantly, by our failures. In that sense, failure isn't just a part of science, it's the very heart of it. Curiosity has always been the spark that ignites discovery. It's the restless urge to ask why, to poke at the edges of what we know, and to venture into the unknown. In physics, curiosity isn't just a trait, it's a necessity. It's what drives scientists to peer into the depths of black holes, to unravel the mysteries of quantum particles, and to question whether the laws we've come to rely on are as unshakable as they seem. Without curiosity, we might still believe the universe revolves around the Earth or that atoms are the smallest building blocks of matter. It's curiosity that propels us forward, challenging the status quo and daring us to imagine a universe where the rules aren't set in stone. At its core, curiosity is about questioning the familiar. Take gravity, for example. For centuries, Newton's law of universal gravitation was seen as the final word. But curiosity didn't stop there. Scientists like Einstein asked, what if gravity isn't a force at all? This led to the revolutionary idea that gravity is the curvature of space-time, a concept that completely reshaped our understanding of the cosmos. Curiosity doesn't just accept the answers we have, it pushes us to ask better questions, to dig deeper, and to uncover the hidden layers of reality. And sometimes, those questions lead us to radical ideas, like the possibility that the laws of physics aren't laws at all, but more like guidelines, adaptable and malleable. But curiosity isn't just about asking questions, it's about embracing uncertainty. In science, the most groundbreaking discoveries often come from moments of confusion or contradiction. When experiments don't go as planned or observations defy our expectations, curiosity steps in, urging us to explore the unexpected. For instance, the discovery of dark energy came from a surprising observation. The universe isn't just expanding, it's accelerating. This wasn't what anyone expected, but instead of dismissing it, scientists leaned into the mystery, driven by curiosity to uncover what lies beyond our current understanding. It's this willingness to sit with uncertainty, to explore the gaps in our knowledge, that leads to the most transformative breakthroughs. Curiosity also thrives on collaboration. Some of the most profound questions in physics, like the nature of time, the origins of the universe, or the behavior of quantum particles, require perspectives from multiple disciplines. Mathematicians, philosophers, engineers, and even artists bring unique insights that can spark new ideas and challenge old assumptions. It's through this collective curiosity that we begin to see the bigger picture, realizing that the laws of physics might not be isolated truths but part of a larger, interconnected framework. This collaborative spirit reminds us that curiosity isn't just an individual pursuit. It's a shared journey, one that brings us closer to understanding the universe in all its complexity. Yet, curiosity isn't without its challenges. It requires us to step outside our comfort zones to confront ideas that might seem strange or even unsettling. The idea that the laws of physics might be mere suggestions, for example, can feel disorienting. It challenges the very foundation of how we understand reality, suggesting that the rules we've come to rely on might not be as fixed as we thought. But it's precisely this kind of radical thinking that curiosity inspires. It encourages us to imagine a universe where the impossible becomes possible, where the boundaries of what we know are constantly shifting. And in that shift lies the potential for discovery, for uncovering truths that might have remained hidden if we'd been too afraid to ask. Ultimately, curiosity is what keeps science alive. It's the force that drives us to explore, to experiment, and to dream. It's what reminds us that the laws of physics aren't just rules to be memorized, they're invitations to explore, to question, and to imagine. And as we continue to push the boundaries of our understanding, one thing is clear: the universe is far more mysterious, far more dynamic, and far more wondrous than we've ever dared to imagine. Curiosity isn't just the key to unlocking its secrets, it's the very essence of what it means to be human. Science thrives on skepticism, not the kind that dismisses ideas outright, but the kind that asks, how do we know this is true? It's a mindset that doesn't take anything for granted, not even the laws of physics themselves. After all, what if the rules we've come to rely on aren't as unbreakable as we've been led to believe? Skepticism isn't about tearing down ideas. It's about testing them, refining them, and sometimes even replacing them when the evidence demands it. And when it comes to physics, where the stakes are as vast as the cosmos itself, this kind of rigorous questioning is absolutely essential. Let's start with a simple example: gravity. For centuries, Newton's law of universal gravitation was accepted as fact. It explained everything from the motion of planets to the fall of an apple with remarkable accuracy. But then came skepticism, questions like, why does gravity work this way? And what if there's more to it? These weren't idle musings, they were the seeds of a revolution. Einstein's theory of relativity didn't just refine Newton's ideas, it completely reimagined gravity, showing that it's not a force in the traditional sense but a curvature in the fabric of space-time. This shift didn't happen because Einstein was content with the status quo. It happened because he dared to question it. Skepticism also plays a crucial role in uncovering the gaps in our understanding. Take dark matter and dark energy, for instance. These mysterious entities make up the vast majority of the universe, yet we can't see them or directly detect them. How do we know they exist? Because the universe behaves in ways that our current laws of physics can't fully explain. Galaxies spin faster than they should, and the universe's expansion is accelerating phenomena that don't fit neatly into the frameworks we've built. Skepticism pushes us to ask, what are we missing? And could our assumptions be wrong? It's this willingness to question that keeps science moving forward, even when the answers are elusive. But skepticism isn't just about finding flaws in existing theories, it's also about opening the door to new possibilities. Consider the idea that the laws of physics might not be absolute. What if they're more like guidelines shaped by the conditions of the universe itself? This isn't just a wild guess, it's a hypothesis born out of skepticism. When we look at the strange behavior of particles at the quantum level or the extreme conditions near black holes, we see hints that the rules we take for granted might break down in certain contexts. Skepticism encourages us to explore these anomalies, to ask whether the laws we've discovered are universal truths or just one piece of a much larger puzzle. Of course, skepticism isn't always comfortable. It challenges us to confront the limits of our knowledge, to admit that we don't have all the answers. But it's precisely this discomfort that makes it so powerful. By questioning our assumptions, we create space for new ideas to emerge. We allow ourselves to imagine a universe that's far more flexible, far more dynamic, and far more mysterious than we've ever dared to believe. And in that space, we find the potential for discovery not just of new facts, but of entirely new ways of thinking about reality. So, what does skepticism mean for the future of physics? It means that the laws we've uncovered aren't the final word, they're a starting point. They're the foundation upon which we build, but they're also the questions we keep asking. Skepticism reminds us that science isn't about arriving at the truth. It's about the journey of seeking it. And as we continue to explore the mysteries of the universe, one thing is clear: the laws of physics aren't set in stone. They're more like signposts pointing us toward a deeper understanding of a cosmos that's always full of surprises. What is it about the unknown that captivates us so deeply? From the flicker of a candle flame to the swirling galaxies light years away, wonder has always been the spark that ignites our curiosity. It's that feeling of awe, that irresistible pull to uncover what lies just beyond our understanding. Wonder isn't just a fleeting emotion, it's the driving force behind some of the most profound discoveries in physics. It's what compels us to ask questions that seem impossible, to challenge the rules we thought were unbreakable, and to imagine a universe where even the laws of physics might be more flexible than we've ever dared to believe. At its heart, wonder is about embracing the unknown. It's about looking at the night sky and not just seeing stars, but sensing the vast, unexplored expanse that stretches beyond them. When Galileo first turned his telescope to the heavens, he didn't just observe celestial bodies, he ignited a revolution in how we see the cosmos. His sense of wonder didn't just lead to new discoveries, it reshaped our very understanding of reality. And that's the power of wonder. It doesn't just accept what's already known, it pushes us to explore what's possible. This spirit of wonder is what fuels radical theories in physics. Take the concept of quantum entanglement, for example. At first glance, the idea that two particles can instantaneously influence each other across vast distances seems impossible. Yet, it's precisely because of this strangeness that physicists are captivated by it. Wonder drives us to ask, how can this be? And what does it mean for the nature of reality? It's this relentless questioning that leads to breakthroughs, challenging the very foundations of what we thought we knew. But wonder isn't just about asking questions, it's about being open to the answers, no matter how unconventional they might seem. Consider the multiverse theory, which suggests that our universe might be just one of many. It's a bold idea, one that stretches the limits of our imagination. Yet, it's born out of wonder, out of the desire to explain why our universe seems so finely tuned for life. Could it be that the laws of physics aren't fixed but vary across different universes? This kind of thinking doesn't just challenge our assumptions, it invites us to see the universe as a place of infinite possibilities. Wonder also reminds us that science isn't just about facts and figures, it's about the stories we tell about the universe. When we look at a black hole, we don't just see a region of intense gravity, we see a mystery waiting to be unraveled. What happens beyond the event horizon? What secrets does it hold? These questions aren't just scientific, they're deeply human. They connect us to the cosmos in a way that transcends equations and experiments, reminding us that the pursuit of knowledge is as much about wonder as it is about understanding. And then there's the role of wonder in challenging our perceptions of the laws of physics. Could it be that the rules we've come to rely on, gravity, electromagnetism, even the speed of light, aren't absolute truths but mere approximations? This isn't just a philosophical question, it's a practical one. Wonder drives us to explore the edges of our knowledge, to test the limits of our theories, and to consider that the universe might be far more dynamic and unpredictable than we've ever imagined. It's through this lens of wonder that we begin to see the laws of physics not as rigid rules but as flexible guidelines, shaped by the conditions of the cosmos itself. So, what does wonder teach us about the universe? It reminds us that the unknown isn't something to fear, it's something to embrace. It's through wonder that we find the courage to explore, to question, and to imagine. And as we continue to push the boundaries of our understanding, one thing becomes clear: the universe is far more mysterious, far more beautiful, and far more wondrous than we've ever dared to imagine. In the end, it's not just about discovering the laws of physics, it's about embracing the journey of discovery itself, with all its surprises, challenges, and infinite possibilities. In the grand quest to understand the universe, there's a trait that often goes overlooked but is absolutely essential: humility. It's the quiet acknowledgement that no matter how much we learn, our understanding will always be incomplete. Humility reminds us that the cosmos is vast, complex, and often beyond our current grasp. It challenges us to question not just the answers we've found, but the very questions we're asking. And when it comes to physics, a field built on the pursuit of universal truths, humility is the key that keeps the door open to new possibilities, even when they defy everything we thought we knew. Take the history of physics as an example. For centuries, Newton's laws of motion were seen as the ultimate description of how the universe works. They explained everything from the orbits of planets to the trajectory of a thrown ball with such precision that it seemed there was nothing left to discover. But then came Einstein, who showed that Newton's laws, while incredibly useful, were only part of the story. His theory of relativity revealed a deeper, more intricate reality, one where space and time are interwoven and gravity isn't a force but a curvature. This shift didn't just refine our understanding, it completely transformed it, and it happened because scientists were humble enough to admit that even the most elegant theories might not tell the whole story. This kind of humility is especially crucial when we explore radical theories, ideas that challenge the very foundations of what we think we know. Consider the concept of dark energy, which makes up a staggering 68% of the universe. We don't know what it is or how it works, but its existence forces us to confront the limits of our understanding. Instead of clinging to the familiar, humility allows us to embrace the unknown, to ask questions that might seem unanswerable, and to consider that the laws of physics as we know them might be just one piece of a much larger puzzle. Humility also plays a vital role in how we approach experimentation and discovery. When scientists design experiments, they often start with a hypothesis, a best guess based on what they already know. But humility reminds them to remain open to the possibility that their hypothesis might be wrong. This openness is what led to some of the most groundbreaking discoveries in physics. For instance, the discovery of quantum mechanics didn't come from proving existing theories right. It came from observing phenomena, like the photoelectric effect and particle-wave duality, that defied classical explanations. Humility allowed physicists to set aside their assumptions and explore a completely new framework, one that has since revolutionized our understanding of the universe. But humility isn't just about acknowledging what we don't know. It's also about recognizing the limits of our tools and methods. Even the most advanced technologies like particle accelerators and space telescopes have their constraints. They can only measure what they're designed to measure, and they can only observe phenomena within certain parameters. Humility reminds us that there might be aspects of the universe, entire dimensions, forces, or particles that are beyond our current ability to detect or understand. This isn't a failure, it's an invitation to keep exploring, to keep pushing the boundaries of what's possible. At its core, humility is a reminder that science is a journey, not a destination. It's a process of constantly refining our understanding, of admitting when we're wrong, and of staying curious even when the answers seem out of reach. It's what allows us to consider that the laws of physics might not be fixed and unchanging, but rather dynamic and adaptable, shaped by the conditions of the universe itself. In this view, the laws we've discovered aren't the final word. They're a starting point, a foundation upon which we can build new ideas and explore new frontiers. So, as we continue to unravel the mysteries of the cosmos, let's carry humility with us. Let's embrace the idea that the universe is far more complex, far more mysterious, and far more wondrous than we've ever imagined. And let's remember that the laws of physics as we know them might not be the ultimate truths, they're more like signposts, guiding us toward a deeper understanding of a reality that's always full of surprises. In the end, it's not about having all the answers, it's about having the courage to keep asking the questions, and that's where the real adventure begins. What does it take to step into the unknown, to question the very foundations of what we think we know? It takes courage, not the kind that battles dragons or scales mountains, but the kind that dares to challenge the status quo, to ask questions that might seem unanswerable, and to imagine possibilities that defy conventional wisdom. In the realm of physics, courage isn't just a virtue, it's a necessity. It's the spark that ignites radical theories, pushing us to explore ideas that might seem impossible at first glance. Without courage, we'd still be trapped in the comfort of what we know, never daring to venture beyond the boundaries of our understanding. Think about the great leaps in physics throughout history. Each one began with a courageous question. What if the Earth isn't the center of the universe? What if time and space aren't separate but intertwined? What if particles can be in two places at once? These questions didn't just challenge existing theories, they shattered them, opening up entirely new ways of seeing the world. Courage is what allows us to embrace the unthinkable, to consider that the laws of physics might not be as rigid as we've been led to believe, but more like guidelines open to interpretation and change. But courage isn't just about asking big questions, it's about being willing to follow them wherever they lead, even if the answers are unsettling. Take the concept of the multiverse, for example. The idea that our universe might be just one of many is both exhilarating and humbling. It challenges us to rethink our place in existence, to consider that the laws we've come to rely on might not be universal truths but local rules specific to our corner of reality. This kind of thinking requires a certain boldness, a willingness to let go of what we thought was certain and embrace the uncertainty of the unknown. Courage also plays a crucial role in how we test and validate radical ideas. When Einstein proposed his theory of general relativity, it wasn't immediately accepted. It took years of experimentation, observation, and debate before it became the cornerstone of modern physics. The same is true for quantum mechanics, which was initially met with skepticism and resistance. But it was the courage of scientists to pursue these ideas despite the pushback that led to some of the most profound discoveries in history. It's a reminder that progress often requires stepping into the unknown, even when the path ahead is unclear. And then there's the courage to admit when we're wrong. Science is built on the principle of falsifiability, the idea that any theory, no matter how well established, can be proven wrong. This means that even the most respected scientists must be willing to question their own assumptions and abandon ideas that no longer hold up. It's not easy to admit that something you've spent years studying might be incomplete or incorrect, but it's essential for the advancement of knowledge. This kind of intellectual humility, rooted in courage, is what keeps science moving forward. So, what does all this mean for the laws of physics? Courage reminds us that these laws aren't static or unchanging, they're dynamic, evolving frameworks that reflect our current understanding of the universe. They're not the final word, but a starting point, a foundation upon which we can build new ideas and explore new frontiers. By embracing courage, we open ourselves up to the possibility that the universe is far more complex, far more mysterious, and far more wondrous than we've ever dared to imagine. In the end, courage isn't just about facing the unknown, it's about embracing it. It's about recognizing that the journey of discovery is as important as the answers we find along the way. And as we continue to push the boundaries of our understanding, one thing is clear: the laws of physics aren't set in stone. They're more like invitations to explore, to question, and to imagine. And it's through courage that we accept those invitations, stepping into a universe that's always full of surprises. What does it take to turn a seemingly insurmountable challenge into a groundbreaking discovery? The answer lies in persistence, the quiet, unyielding determination that drives scientists to keep pushing forward, even when the path ahead is riddled with obstacles. In the world of physics, where the questions are as vast as the cosmos itself, persistence isn't just a virtue, it's a necessity. It's what allows us to confront technical hurdles, navigate theoretical roadblocks, and ultimately challenge the very notion that the laws of physics are set in stone. Without persistence, the greatest discoveries in science might never have seen the light of day. Consider the story of the Higgs boson, often referred to as the God particle. The search for this elusive particle spanned decades, involving thousands of scientists, billions of dollars, and one of the most complex machines ever built, the Large Hadron Collider. There were moments when the quest seemed futile, when the technical challenges felt overwhelming, and when skeptics questioned whether the Higgs even existed. But the scientists persisted, refining their methods, improving their detectors, and never losing sight of their goal. When the Higgs boson was finally discovered in 2012, it wasn't just a triumph of technology, it was a testament to the power of persistence. It showed that even the most daunting challenges can be overcome with relentless determination. But persistence isn't just about overcoming technical hurdles, it's also about wrestling with theoretical roadblocks. Take the quest for a unified theory of physics, for example. For decades, scientists have been trying to reconcile the two great pillars of modern physics, quantum mechanics and general relativity, into a single, coherent framework. The problem is, these two theories operate under entirely different rules. Quantum mechanics governs the tiny world of particles, where uncertainty reigns, while general relativity describes the vast cosmos, where space and time bend under the weight of massive objects. Bridging these two worlds has proven to be one of the most difficult challenges in the history of science. Yet, physicists persist, exploring radical ideas like string theory and loop quantum gravity, each step bringing us closer to a deeper understanding of the universe. What's fascinating about persistence is how it challenges our understanding of the laws of physics themselves. When faced with phenomena that don't fit neatly into our existing frameworks, like dark matter, dark energy, or the strange behavior of particles at the quantum level, persistence pushes us to ask, what if the rules aren't as fixed as we thought? This kind of thinking doesn't just refine our theories, it opens the door to entirely new ways of seeing the universe. It suggests that the laws of physics might not be universal truths, but rather emergent properties, shaped by the conditions of the cosmos itself. In this view, persistence isn't just about solving problems, it's about reimagining the very nature of reality. And then there's the role of persistence in fostering collaboration. Scientific discovery is rarely the work of a single individual. It's a collective effort built on the shared determination of countless researchers around the world. When one team hits a roadblock, another picks up the torch, bringing fresh perspectives and new approaches. This collaborative persistence is what drives progress, allowing us to tackle challenges that would be impossible to overcome alone. It's a reminder that science is a shared journey, one that requires not just individual tenacity, but a collective commitment to pushing the boundaries of knowledge. So, what does persistence teach us about the laws of physics? It reminds us that our understanding is always evolving, shaped by the challenges we face and the determination we bring to solving them. The laws we've uncovered aren't the final word, they're a starting point, a foundation upon which we can build new ideas and explore new frontiers. And as we continue to push the boundaries of our understanding, persistence becomes not just a tool but a mindset, a way of embracing the unknown, confronting the impossible, and finding beauty in the journey of discovery. After all, the universe doesn't give up its secrets easily, but with persistence, we might just uncover the truths that lie just beyond our grasp. Imagine trying to solve a puzzle, but every time you think you've found the right piece, someone tells you the entire picture might be different. That's the essence of open-mindedness in physics, a willingness to question what we think we know and to embrace the possibility that reality might not follow the rules we've always assumed. It's not about rejecting established ideas outright. It's about being flexible enough to consider that the laws of physics, as we understand them, might be more like guidelines than unbreakable truths. This mindset is crucial when exploring radical theories, where the answers often lie outside the boundaries of conventional thinking. Open-mindedness has always been the driving force behind scientific breakthroughs. Take the shift from Newtonian physics to Einstein's theory of relativity. At the time, Newton's laws were seen as the definitive explanation of how the universe worked. But Einstein dared to imagine a different reality, one where space and time were intertwined, and gravity wasn't a force but a curvature in the fabric of the cosmos. This wasn't just a leap of logic, it was a leap of open-mindedness, a willingness to challenge the status quo and explore ideas that seemed at first almost absurd. Without this flexibility, we might still be stuck in a universe where time and space are separate, unchanging entities. But open-mindedness isn't just about accepting new ideas, it's also about questioning the old ones. Consider the concept of dark matter. For decades, the behavior of galaxies suggested that something invisible was influencing their motion. Instead of dismissing this as a fluke or a measurement error, scientists remained open to the possibility that our understanding of gravity, or even the universe itself, might be incomplete. This openness led to one of the most profound discoveries in modern cosmology, reshaping our understanding of the cosmos and reminding us that the laws we've come to rely on might only describe a small part of the story. This willingness to question and explore is especially important when dealing with radical theories. Take string theory, for example. It proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. At first glance, this idea seems far-fetched, even fantastical. Yet, open-mindedness allows scientists to take it seriously, to explore its implications and to test its predictions. Even if string theory ultimately proves to be incorrect, the journey of exploring it has already led to new mathematical tools and insights that have advanced other areas of physics. It's a reminder that open-mindedness isn't just about finding answers, it's about asking better questions. And then there's the role of open-mindedness in challenging our assumptions about the laws of physics themselves. Could it be that the rules we've discovered aren't universal truths but context-dependent guidelines? For instance, the laws that govern the behavior of particles at the quantum level are very different from those that apply to everyday objects. This suggests that the laws of physics might not be fixed and unchanging, but could vary depending on the scale or environment. Open-mindedness allows us to consider this possibility, to explore what it means for our understanding of reality, and to remain curious about the deeper truths that might lie just beyond our current grasp. So, why does open-mindedness matter so much in physics? Because it's the key that unlocks new ways of seeing the universe. It's what allows us to move beyond the familiar and explore the unknown, to challenge the rules we thought were unbreakable, and to imagine a reality that's far more dynamic and mysterious than we've ever dared to believe. In the end, open-mindedness isn't just a trait, it's a tool, one that helps us navigate the ever-shifting landscape of scientific discovery and uncover the deeper truths that shape our understanding of the cosmos. And as we continue to explore, one thing becomes clear: the laws of physics might not be as rigid as we once thought. They're more like invitations, waiting for us to step through and discover what lies beyond. What happens when brilliant minds come together to tackle the universe's greatest mysteries? Collaboration isn't just a buzzword in science, it's the lifeblood of discovery. In physics, where the questions are as vast and complex as the cosmos itself, no single person or discipline can hold all the answers. It's through collaboration that we're able to piece together the puzzle of reality, combining diverse perspectives and expertise to uncover insights that might otherwise remain hidden. And when it comes to exploring radical ideas like the possibility that the laws of physics aren't as fixed as we've assumed, collaboration becomes not just helpful but absolutely essential. Think about the monumental challenges physicists face today. From unraveling the mysteries of dark matter to reconciling quantum mechanics with general relativity, these aren't problems that can be solved in isolation. They require a symphony of minds: theorists, experimentalists, mathematicians, and even engineers, each bringing their unique skills to the table. Take the Large Hadron Collider, for example. This massive project, which led to the discovery of the Higgs boson, involved thousands of scientists from over 100 countries. It wasn't just about building a machine, it was about pooling knowledge, sharing ideas, and working together to push the boundaries of what we thought was possible. Collaboration made this monumental achievement possible, and it continues to drive progress in physics today. But collaboration isn't just about solving technical challenges, it's also about challenging assumptions. When physicists with different backgrounds and perspectives come together, they bring fresh ways of looking at old problems. For instance, the interplay between theoretical physicists and observational astronomers has been crucial in understanding phenomena like black holes and gravitational waves. Theorists might propose a model, but it's the astronomers who test it against real-world data. This back and forth not only refines our understanding, but also opens the door to new questions and ideas. It's through this dynamic exchange that we begin to see the laws of physics not as rigid rules, but as flexible frameworks, shaped by the interplay of observation and theory. Collaboration also encourages us to think beyond the boundaries of our own disciplines. Physics doesn't exist in a vacuum. It's deeply connected to fields like mathematics, computer science, and even philosophy. For example, the development of string theory, which attempts to unify the fundamental forces of nature, has relied heavily on advanced mathematics. Similarly, the study of quantum computing has brought physicists and computer scientists together to explore the potential of harnessing quantum mechanics for practical applications. These cross-disciplinary partnerships remind us that the laws of physics aren't just about particles and forces, they're part of a larger, interconnected web of knowledge. Perhaps most importantly, collaboration fosters a culture of openness and curiosity. When we work together, we're more willing to question the status quo and explore radical ideas. The concept that the laws of physics might not be fixed, for instance, is something that requires a collective leap of imagination. It's not enough for one person to propose the idea. It takes a community of thinkers to test it, refine it, and ultimately decide whether it holds up. This collaborative spirit is what allows us to push the boundaries of our understanding, to consider possibilities that might seem far-fetched at first, and to remain open to the idea that reality might be far more flexible than we've ever imagined. So, what does collaboration teach us about the laws of physics? It shows us that our understanding is always evolving, shaped not just by individual brilliance but by the collective effort of countless minds working together. The laws we've discovered aren't the final word, they're a starting point, a foundation upon which we can build new ideas and explore new frontiers. And as we continue to collaborate, to share our knowledge and challenge our assumptions, we're reminded that the universe is a place of infinite possibilities, full of mysteries waiting to be uncovered. In the end, it's not just about what we know, it's about how we come to know it together. As we come to the end of this exploration, one thing is clear: the idea that the laws of physics might not be as rigid as we've been taught is more than just a fascinating thought experiment. It's a gateway to reimagining the universe itself. From the strange, unpredictable behavior of particles at the quantum level to the mind-bending possibilities of alternate dimensions and multiverses, these radical theories don't just challenge our understanding, they invite us to see reality in a completely new light. They remind us that science isn't about finding absolute truths, but about asking better questions, pushing boundaries, and staying curious. What makes this journey so thrilling is that the answers are still out there, waiting to be discovered. Whether it's unraveling the mysteries of dark matter, probing the nature of time, or exploring the edges of space and gravity, every step forward brings us closer to understanding the cosmos in ways we can't yet predict. And while we may not have all the pieces of the puzzle yet, the process of piecing them together is what makes science so extraordinary. It's a reminder that the universe is not a static, unchanging entity but a dynamic, evolving system, full of surprises and secrets waiting to be uncovered. So, as we wrap up this dive into the radical theories reshaping physics, let's not forget the most important takeaway. The laws of physics as we know them might not be the final word. They could be more like signposts guiding us toward a deeper understanding of a reality that's far more flexible, far more mysterious, and far more wondrous than we've ever dared to imagine. And that's what makes this journey so exciting. It's not just about the destination, it's about the discoveries we make along the way. Thank you for joining us on this adventure through the frontiers of science. If you enjoyed this exploration, don't forget to like, subscribe, and share your thoughts in the comments below. What do you think about the idea that the laws of physics might be mere suggestions? The conversation doesn't end here, it's just beginning. Until next time, keep questioning, keep imagining, and keep exploring the infinite possibilities of the universe. The cosmos is full of surprises, and who knows what we'll discover next.